One slide.
Okay, and while we're waiting for that, just a quick reminder to everybody, in case you haven't seen the text chat in the chat box, we are recording the session. We'll post this to our YouTube by early next week. And if you would like, you can join our Slack channel. The link to that is in the chat box.
Okay. You can get one more when we now start. There we go, we got one more. Okay. Good morning, everybody. It's 9 o'clock in the morning in Seattle, and it's a cloudy day, but it's going to brighten up later on. There'll be lots of sun. I hope the weather is good where you are. So let's begin today. I'll share my screen in a second. I'll just show you what we're doing today. This is the schedule for today. So we're going to start off with Lucian, who's the lead developer on Roadrunner and biomodels work, a lot of reproducibility. So he has a lot of expertise in these areas. So Lucian's going to start off with some biomodels and reproducibility. I thought then maybe we'd have a discussion time for 15 minutes. We'll see how that goes. I know everybody's very shy, but we'll see what we can do there. And then Joe Hellerstein, as I said, faculty from eScience, a lot of experience in computational work. We'll be doing some parameter fitting theory. Then we'll have a little break, and then I'll take over for a little bit to do some parameter fitting. And I'm going to try and build a program live to show how you can fit models to data using Roadrunner. And then we'll have another discussion time and see how that goes. Then we have a lunch break. And then we'll dive into some AI. So Joe gives some theory, but he also, both me and him will be giving some practice work on the AI and show you how you can do the parameter fitting work I did in the morning, how you can do it using AI instead. Okay, so that's what we're going to do today. Okay, so over to you, Lucian.
All right, we are on day 2 of the Google Drive, and I'm going to put a link to this directly in the chat. There we go. Put the chat over there so I can see it. So I'm talking about biomodels and reproducibility. So I'll be going through those two things. And then if there's time, so first of all, I'm going to talk about biomodels, like pulling down some biomodels and like examining them, then seeing how they can be, the results that they have to create the figures in them can be reproduced on different platforms. And then if there's time, I'll like ask you, like, what area are you, is one of you researching? So if you have something that you're like, oh, I'm researching, I don't know, I'm researching COVID, I want to like look at some COVID models, we can do that as well. So I just did my little pip install Tellurium, so we don't have to wait for that. Biomodels, here, let me go to biomodels.net. Sometimes this works for me and sometimes it doesn't. Oh, look, this is not working right now. If you look for biomodels, you get it here. So usually biomodels.net takes you to this, at the ebi.acb.uk biomodels. It is a curated database of models that reproduce figures from published papers. There are basically 3 branches: the manually curated branch, the non-curated branch, and the auto-generated branch. The manually curated branch is the one we're going to be talking about. That's the one where curators have gone through and made sure that they can create a model almost always an SBML that will reproduce at least one of the figures from that paper. The non-curated branch is models that are in some stage of getting curated. Like if an author might like directly like put a model up on biomodels and say like this works, but it hasn't been fully curated yet. One of the things that the curators try to do is annotate the models so they can say like this is from yeast, this is Saccharomyces, this particular enzyme is this particular species is magnesium or whatever. That makes searching biomodels a little bit easier and more robust. And then the auto-generated branch are models that have been auto-generated, obviously, from like massive amounts of data. The auto-generated models tend to be very, very large and not parameterized. So you get the basic structure of your model, like what interacts with everything else without knowing the rate at which any of that happens. So if you go to the manually curated branch, you can click on it. You can do searches here. Yeah, I don't know if this actually works. I think that might be kind of broken. So if you wanted to look for iron or something, yeah, let's see. Let's change that to and quote. Is that going to work? Nope. Okay, I'll just look for
Lucian.
iron instead.
Lucian, my experience with this is just try iron. Yeah, try that.
Okay. And then if you want the manually curated ones, you can click that and then it'll pull it in. So, so there's 11 models that have iron in them somewhere. Obviously, iron is probably not the easiest thing to like. You're probably not doing actual research on iron itself, but here we have a variety of models with that. So here is one model that I happen to know is already in biomodels. It's the Jana Wolf model on metabolism in yeast. This picture is basically what their model is. So every arrow in this picture is a reaction. Obviously, it's a two-compartment model here. You have your submodel, and then you're probably like I haven't looked at this. I assume this is like the cell and then like the mitochondria or something. But so the
looks like some kind of vacuole.
Yeah, it could be a vacuole. I don't know. Probably should have looked that up more. But anyway, metabolism, that's the main thing. So if you know if you've looked for the model, in fact, let's see here. Mathematical analysis. Let's go ahead and do a search. Mathematical analysis. Nope. Is it going to do that? No, it's something like that.
You spelled mathematical wrong.
There we go. Yeah, there we go. That's it. Wolf 2001, biomodels 90. So when you're looking at a particular biomodels, it'll show you once you get a particular one. If you know which one it is, you can click on any of them and just edit this number up here. But anyway, here we are, biomodels 90. This is a short description of what it is. Usually it'll like pull the abstract from the paper into here. It'll have a link to the paper itself, which I will load here.
It is a mitochondria.
Yeah, it is the mitochondria. Okay, yay. And then you see like these other tabs here. So the files are like all the different files that are associated with it. The top model one is the model itself. It is the SBML version of the file. SBML we've sort of alluded to over the course of our time here. SBML is what Antimony translates to. It is actually the format that Roadrunner reads natively. When you write an Antimony model in Tellurium, behind the scenes, it'll translate it to SBML and send it to Roadrunner. So here we're going to send that model directly to Roadrunner. You can see from the history, that like recently, like I updated things because I updated literally all the biomodels with better SetML, which I'll talk about in a bit. These are the things that, these are the elements that they pulled out and they said are particularly important in the model, NADH, NAD+. And the other particularly interesting part of the figure is going to be, or part of this is going to be the curation tab. The curation tab will tell you in words and in a picture what the curator originally did to reproduce a figure from the paper. So this figure is usually something that was exported from a particular program. In this case, they used a program called ODE Solver to read the SBML program and read the SBML model and export this. Herbert was talking about how there's like old programs don't survive. Like if you used a program 10 years ago, you probably have to use a different program today. I don't think ODE Solver is around anymore. I don't know.
Yeah,
Probably
no,
not.
no idea. Yeah, probably not.
So this is, it says it's figure 2 from the paper. So let's look at the paper. Let's see if we can get the full text. There we are. There's our figure 1 of the figure. These are all the SDTs that was translated into V1, V2, V3, etc. Like those are the actual reactions in the paper. And here is figure 2. And so there are, the time goes from 0 to 100. There's a variety of things that go sort of like pulse a few times, and other things that do that less. And here we have the things pulsing, going from 0 to 100, and other various things moving around. So I'll trust the only issue. So we're going to talk about reproducibility. And one of the problems with reproducibility from a figure is that the numbers that went into making this figure are not around. So what you have to do is that, can I zoom in? Yeah, let's do that. Like this doesn't even have units on this left axis. It's just like there are arbitrary units. Things go up and down. So like figuring out if you have actually reproduced this figure is actually kind of difficult. Like maybe they go in this pattern, but like were they the same numbers that originally were over there? Maybe, maybe not. Are all these on the same scale? Are they on different scales? These are the sorts of questions that you're not necessarily sure of when you're trying to reproduce someone else's work. And why it's important to include as supplementary data, hopefully, at least the numbers from your figures, if not like the actual SBML model that you use to create it. So all that to say, it's difficult. So that's the curation tab. That was the program and stuff they used to use it. So let's see if we can reproduce what's going on in here. So if we go to the Wolf model, if we go to the Files tab, you can download this model directly with this link. So I'm going to copy this link and I'm going to go to the biomodels demo, and I've already put this in here, but so it's probably all the same. But if I can say te.load SBML model, or I can just say load s, short for SBML, oops, and put in that model that we just put, that link that we just copied. We're going to simulate from 0 to 100 with 1,000 time points and plot time versus oxy. And then we're going to plot, and this like gave me some X labels and Y labels just to like add things to that. So let's see if we can do that. And bam, we do indeed get it. So that was oxy. If we look here, curation tab, oxy was this flat line, which I guess is this. So sort of slightly go up and then bounce. Let's see here. This is greatly reduced. You'll notice the scale is from 6.2 to 7.6. So if you were to smush this, it would look a slightly different, slightly more like this thing. But yeah, 6 to 7.2, that seems about right. It sort
I
of
think you can
trails up.
change. You
Yeah.
can change the Y scale.
Yeah, sure.
plot,
Let's
I
do
think.
that.
Why not? Task
Let's see. Do you remember what the
it
argument
might
is?
be Y lim or something.
Oh yeah.
There it is.
Y lim, is it? Oh
Might
yeah, sure.
be.
Let's try it. Equals 0 to 10. Let's try that. Hey, yeah. Oh, nice. So there we go. You change your Y limit, and it actually like works better. I'll admit some people here while I'm waiting. All right.
Yeah, that looks more like the original.
Yeah, it looks more like the original paper. All right. So hey, there it is. It's reproduced. For this, we're gonna look at like all of the different floating species in here. And we've exported to a wolf.txt file. So here's the wolf.txt file. We're looking at all the different things, and then we're going to, you know what? Whatever. I was going to clear all the things, but so here we have like all of the different things, and now we have even more elements than were in that original figure, although it may be sort of split over 2 different things. Obviously there's something that like goes way up and down that didn't show up in this one.
Can you explain why you converted it to antimony?
Antimony, just so that we can look at it.
But why couldn't you look at it with the sbml?
Well, let's look at it with the sbml. Let's actually, here we can just look at it directly from here. If we go to the files and we look at it, this is what sbml looks like.
No. I mean, why couldn't you have done that plot with sbml? Why did you have to convert
can.
it to antimony?
Sorry, say that again.
What was the reason for converting it to antimony? Why couldn't you have done the same thing with sbml?
It started off as sbml. We just did it to antimony. We're going to look at it in a little bit. That's all.
Oh.
We're like just for viewing it. Yeah, it started off as sbml. It's native sbml. It went straight to Roadrunner's sbml. That's like the most robust way of doing things. Pulling things into Antimony just means like you don't have to look at this, because this is the actual like sbml model. So like these are the notes. Here's a bunch of like annotations and stuff, and like this is talking about a particular species. So here's where ETH. I know what I'm looking for, so I could like say like, oh yeah, here that's the key word here, species, initial concentration of 7, O2. So this is like oxygen, starts off at 7, and then it has some annotations around it and stuff. As we go down past the species, we're going to get to parameters, which are just numbers. You have some rules. I remember I talked to you about assignment rules the other day. And then here's our reactions. And again, like, so this, I can look at this and say like, oh, Sol plus A3C goes to at APS plus PPI. Those are reactants, those are your products. And this is the reaction rate. It's in MathML, like times, like it's those 4 things multiplied by each other. But there's no need to worry about looking at the sbml, because that's what Antimony was designed for, is so you can actually look at things.
No, I'm curious why. I mean, somebody looking at this must think in order to plot everything, you have to convert it to antimony.
Oh, no, you don't need to. We can, we could just say, like even here. Wait, what happened here? Oh, somehow how did that? Oh, well, anyway. But if we want to set this will, and then instead of giving it this argument, we'll just have the default arguments, and wolf.plot. And then for that, we will go ahead and give it this. Oh, because I already said, because it set the
because it remembers. So this is an
it
important
remembered
point.
what they were.
This actually annoys me sometimes, but
Yeah,
a couple of users will like this. The problem is,
yeah,
to those who are listening, when you use that selection list in the square brackets,
yeah.
it remembers it forevermore unless you tell it to change that. So the only way to do that is to reload the model, actually.
You can probably like set the selection list.
You can, but you have to, yeah, you could.
Or hey, look, there's a reset selection list.
Oh, there is. I didn't even know that.
Let's try that.
I was probably put in because of this.
Because you were like,
no, yeah, no,
hey, look at that.
Yeah.
There it is.
Okay, so that's something to remember. You might fall into that trap. I've done it a few times, where it remembers what you selected before and it keeps on using that selection. But it looks like there's a reset selection list, or you could just reload the model and start again.
Yeah, yeah. Someone asked to look at both.
Yeah.
Are we good?
Yeah.
This is what it looks like. And we're pulling into my Zoom thing here, but so yeah, this is obviously like slightly more readable list of species. It just lists them all here. Am I good? It has a few assignment rules, and then it has a bunch of reactions. Those dollar signs, remember, are boundary species. So those are like EX probably means external. All the external things are boundary species. N1 and S2 are also internal. These are the initializations. And if you remember, I mentioned that Antimony will do units. This is how that happens. Now these are very generic units. These are substance per volume. So obviously that doesn't really tell you much. And that's because in the original model, they didn't really put in particular units. Oh yeah. Someone asks about like, what's the deal with this like equals instead of the other way? The equals arrow means that it is flagged as being irreversible. That doesn't mean it necessarily is irreversible, but it means it's flagged as being that. The thing that determines whether something is actually reversible or not is this equation. If the equation will always stay positive, then it is irreversible. If it can be positive and negative, then it's reversible. By default, I tend to have people use the dashes because you don't know whether like a dash instead of an equals, just because you don't know, or you might change your mind about whether it's reversible. And because there's no way to check if something is actually reversible without actually doing a simulation or like checking all values of every element of the model to see if they can ever go negative, to see if the overall equation ever goes negative. But if you already know that and you say like, yeah, this is irreversible, you can go ahead and do that, and then it sort of flags that in the sbml model as like, oh, it has the reversible flag. If we look at,
but I should add, it has no functional significance though whatsoever.
It has no functional significance. It's just basically an annotation.
Yeah, it doesn't mean anything to the model itself.
Right. It doesn't mean anything mathematically. It just says something extra to a user to say like, oh, this is sort of a one-way reaction. But yeah, there's nothing that will check if I say like -50 or something here. It will carry on and it won't notice because there's no way to validate that against that. There might be some simulators that like go back and check, and like if this ever goes negative, it might flag the user. I don't know of anyone that does. That was more a theory than anything else.
It's a very obscure flag anyway.
Yeah. So, but that's how you would use it if you wanted to. So we're talking about our initializations. All the compartments are size 1, and here's all our variables. Those things are all constant. And then here's our substance per volume means moles per liter in this model, and the substance unit is mole.
Yeah, I should add,
names.
we should
Yeah,
add there's no enforcement of units either.
yeah. There's no enforcement of
So
units.
again, this is just an annotation.
Now, the better thing about units is that you can statically check your model for unit consistency. You can send a program at it and be like, are my units consistent? And it will say, no, this part is wrong. Or it'll say like, I can't check this part because you didn't put units on this. So a lot of people like are very meticulous about their units, and they can check, they can find errors in their model because they run unit validation on their model before
which programs will do that?
Well, I mean, libSbml does it. So you can always just.
Is it comprehensive? I mean,
it's pretty comprehensive. Yeah.
It'll do conversions between units.
Yeah.
Wow.
It should. Yeah. The other thing, it takes a long time. Like a lot of things will like turn off unit checking because it'll like take, I don't know, 2 minutes to just validate the units of your model. And if you already know your units are fine, or if you don't care about your units, then you don't want to spend those 2 minutes when you load to like check them. But yeah, libSbml is the standard library that is used to read SBML and used for simulators and other programs that read and manipulate and store SBML models. For a while, I was on the SBML team and helped the actual model.
I can't imagine it does a comprehensive check though, because it doesn't have all the conversion units like, gram weight to wet weight and so on. Because that varies from organism to organism.
Oh, well, gram weight to is indeed something that it doesn't do, but everything, all like liters to meters cubed or something is in there and stuff.
Yeah.
Gram weight is a weird unit because yeah, that's like that varies for organisms, so you don't know how that changes. And in fact, I remember chatting about doing that with the FBC models, which actually like worry about that sort of thing.
Yeah.
But everything else, I think, standard things, moles to millimoles to liters, seconds, minutes, hours, whatever.
Okay.
Those are all standard. The other thing that is you can't really check comprehensively is like Celsius or Fahrenheit, because those aren't zero based. So when you say, anyway, so you don't know if you're adding 2 degrees, like what does that mean? Like if it were Kelvin, you would sort of know that you're changing the degrees by 5 Kelvin. But if you're not, then the fact that there's an offset is awkward.
Does it do dimensional analysis of the equations?
It should, I think. Yeah.
Well,
again, this is why it takes forever. And like Sarah worked a long time like trying to update these things. But yeah, this is what, so Matthias like uses units extensively in his models. So for just that reason. I mentioned in passing that biomodels adds annotations. And these are what they look like. We saw them sort of in passing when we were looking at the actual SBML model. But this is what it sort of is. So if you like H2O identity this, oh, hey, all I have to do is follow link. Control click. So yeah, this Kebi term is water. Here's a chemical formula for it. And that is true of all these Kebi terms and Go terms. EC codes are usually for enzymes. Here, let's look at one of the enzymes. So this is the enzyme database. And the enzyme is phosphoadenyl sulfate reductase, also known as thioredoxin. So the fact that these models are annotated like this means that if you are studying a particular enzyme, you can find models in the biomodels database and anywhere else if you have a good enough search engine that has this particular EC number. Let's, just in case, is that going to work if I put this in here? Like I might have, I don't know if I can. Yeah, look at that. I put 1848 in there, and it actually found like there's the wolf model that we just had. So here's a bunch of other models that presumably have 1848 in them. They might not, but let's hope that they do, because that's actually 87 models is a lot of models. I would be surprised if there were actually 87 models that all had those in there, but maybe. Oh, they include the automatically generated ones, and that makes more sense. Ah, yeah, and there's only 8 manually curated ones with it in it. Okay, so yeah, maybe that's reasonable. Yeah, they're all yeast, genome scale model. Again, genome scale model. So yeah, genome scale models are going to have that in there somewhere.
Actually, most of them are not yeast, but anyway.
Yeah, they might not be yeast, but we do have some yeast in those things.
There's some yeast thing.
Is so the enzyme itself.
I mean, I think thioreduction is a relatively common enzyme.
Yeah, it comes in a few different things.
Yeah.
It says the enzyme from E. coli will use thioreductions from. Oh, we'll use thioreductions from other species. That's interesting. I don't know what PAPS means, but presumably, if I was more a biologist, then I would know what PAPS was.
Oh, it's the acronym for
for this thing. Okay, yeah, PAPS reductase. Okay. So that's that. That's all the annotations. And then these are annotations for the model itself. And then here at the bottom is the model notes, sort of the human readable version. This is officially in Markdown, so it can translate to and from HTML because it stores it in the model.
Yeah, so one thing to add about Antimony, this is a new thing that was added, was it late last year? Was you can add all this text now directly in the Antimony, and it'll get stored in the SBML.
Yeah.
So before it was really hard to add all this kind of material to SBML. Now it should be
at least somewhat easier. Yeah.
Yeah.
So you'll notice that like individual enzymes have notes also in this model. That's actually somewhat uncommon. This is a excellently annotated model. They have all sorts of things here. Like V10 is oxygen diffusion. Let's look for V10. Yeah. There's oxygen from the external going to oxy. So it's diffusion into your model. And here, let's close that and look back at the top. Yeah, and there's oxygen from the oxygen in the external environment going to oxygen in the mitochondria. Someone asked if we're publishing a model, you put all the links to the substances in the model. Yes, that would be like, ideally you would do that. And it takes a lot of time and effort. And it's one of those things that the payoff is in the distant future. And sometimes like when you're actually making a model, it's like, well, I just want to sort of get this out the door, and you push it out without the annotation. And then it's not as useful as it could have been. But the payoff is if you have good annotations, then it's easier for people to find your model, to reuse your model, to cite your model in their own work. So if you have good annotations, if you publish on biomodels, you are more likely to get your paper cited in the future going forward. That's a little bit esoteric, and it's a little hard to see exactly how much more cited you'll get. There was at least one good study that actually went through and they like, if you're published on biomodels, you get more citations, and the answer was yeah, a bit. So and in general, it just makes your work more useful to others because people can find it and then they can extend it. The other thing that makes it more extendable is the fact that it is in SBML, because I can just now pull it straight into SBML. I could use this as a submodel of something else and just say like, here's the Jan Wolf model. I'm just using it for this part. And then I'm adding this. I'm seeing how that affects the thing I'm actually studying somewhere else.
I should add, we have an active project at the moment running that will allow people to use AI to automatically annotate their models. There might be some human intervention, but the hope is that it'll do like 80 to 90% of the annotation for you, and then you can just have the missing ones.
And in order to get the AI to help, you have to give all your species good names. So like, here's the wolf model. Like the most important part to get that to work is this section, right?
Oh, yeah.
Like C1 is cytosol, C2 is mitochondria. Those are pretty good names. Sol X is SO4X. That's maybe not as great as it could be. If you said like external SO4, that might make it a little bit easier for an AI to annotate. You want these to be like.
Just to add,
Yeah.
sbml lets you have two kinds of names.
Yeah.
What's called an ID. These are the names on the left, which which can be really short. And then it also lets you have what are called display names, which you might want to present to the human. So that's what Lucian is showing you here. And these then can be used by the artificial intelligence to do the automatic annotation. They can figure out what's what.
And also by the human intelligence
And the
to figure
human
out
as
what's
well,
what. Right.
Human as well. Yeah.
Yeah. Like obviously, like the target audience for these names was someone who knows the model, like AC-CoA. Like I know that's probably acetyl-CoA, but like a random person looking at the model will be like AC-CoA. Like, okay, what is that?
I mean, to be honest, the naming here isn't. I don't recommend this naming. You see the lines 141 and 142, N1 and N2. There is no justification to use N1 and N2 as your reactant name, especially since the display names are so short and well known.
Yeah.
You should be using those display names as your IDs.
Yeah. Actually, so in Antimony, you can, if I wanted to change this model, I could say N1 is NAD and N2 is NADH. And that would go through and change them all. Like I can also do a find and replace for N1 and N2. But this also is sort of an Antimony way of, since you have to be able to say, when you have submodels, you can say like this ID in the submodel is the other ID in the other submodel. You can use that for your current model also. You can just say like, basically means is now, N1 is now at ADH or NAD. And then when this exports to SBML, it'll be as if N1 was never used, and it'll always use the NAD term.
Okay.
Yeah. So if you wanted to go through and sort of fix and update things, that's one way to do it.
Okay.
You'll notice that the fact that it's in quotes means that it's a name, and if you don't put it in quotes, that it's the ID.
Oh yeah.
So, all right. So moving on, we've done the figure. We figured out how to reset the selection lists. This was another thing that people. So this was like without scaling things. It went up to 20, and we saw like all the different figures. And then here is print wolf.get antimony. That this is the wolf is our model. We've been calling our models, like the Roadrunner model is RRR in the past. So this one that we just called wolf. And here we have the whole thing. And in fact, actually run this. This is the new, I think the last time this was moved, this was done was a while back. And that's what we were just looking at. So, there. Dun, dun, dun. So, the wolf model is relatively involved. So I thought I'd go for a simpler model. So biomodels 882, and let's follow the link to biomodels 882. This is Bunes 2009. It is the zombie model. So there is actually a model in biomodels that models that from the paper when zombies attack. I'm going to close all my other, whatever. Tabs here, and we can look at this particular one. Actually, I don't know if this is going to work. I think I remember this not working. Yeah, there we go. here's our model of when zombies attack. And here is the basic model. You have susceptible people that are turning into zombies at a particular rate. You have zombies that are dying at a particular rate, and the dead rising from the dead as zombies at a particular rate, and people dying just without ever being zombies at a particular rate. So that's their basic model and it's relatively straightforward and easy to understand what's going on, which is why, and amusing. So let's do this. We'll just load the model and we'll simulate it and plot it. So we see susceptible people dying off and the zombies appearing, and the removal is the dead. And so let's see if that corresponds to a figure here. Dun, dun, dun. And look, 0 to 5. Here we have the zombies, people starting off at 500 and leaving, and zombies are arriving. Another figure here is this, time from 0 to 10. It says the case of no zombies. It says this equilibrium is unstable. So let's try making that one. So we'll load the model. We'll set the zombie lever to 0, and we'll simulate it. Actually, it was from 0 to 10, and plot. Oh, look at that! Actually, like, was it from 0 to 10 in that figure? It was. All right. So in the case of no zombies, it actually is, we're not reproducing that figure. And that makes, well, I don't know. I think they may have like mislabeled it. Like 0 to 5, it actually does do the thing. But, and it seems odd, right? Like if you have no zombies and you're, and like, but you have the appearance of zombies anyway, like where did they come from? And if you go back and look at this, at their model, you'll realize that there's nothing stopping everyone who's dead from rising as a zombie. So it doesn't matter how you died, you're going to rise as a zombie later. So even if you start off with no zombies, like your dead population starts to go up, and then eventually the dead like turn into zombies and rise from the dead. So that's the basic issue with this model, is that all dead rise as zombies. So we can if we simulate longer, indeed we basically like see what we had before. And it's kind of interesting to like push this out even further, because you can see these start to change a little bit. And if we go even further, you'll see like the zombie population is like starting to increase even more. And if we go further, basically, like the dead are reaching a steady state, but zombies are not at a steady state. And if we go back to the original model again, there's this little thing, pi, going to s, and that is a birth rate. So basically, this part of the model is the SI and R part of the model are reaching a steady state, but everyone that's being born is eventually being funneled into the zombie population and just increasing.
Actually, could you do an experiment to show?
Yeah, sure.
Because you say there's no steady state, right? Which is what it looks like. So can you ask it to compute the steady state?
Sure. Let's see what happens. Maximum iterations is exceeded. Yeah.
So it's failed to find the steady state. So this is a useful thing. You can try to ask for the steady state, and it'll tell you if eventually there isn't one by coming back with an error like this saying maximum iterations exceeded.
Right. We could also, here, let's look at this model again. Oh, that's not the one I want. I want the. All right, here, let's do, export to Antimony. Is that going to work? Aha, look at that. Nice. All right. So the birth rate is the compartment times P. So if I set the birth rate, r dot P equals 0, and then I simulate, let's see if I was right about zombies going up forever only because of the birth rate. Oh no, look at that. That's interesting.
Looks like it's plateauing off though.
Yeah, and they're actually they potentially could be in r dot steady state here.
Oh,
So it
Yeah.
still can be able to converge, a slightly different reason, but
yeah.
Now I'm curious. So this is the sort of thing that's nice to do. Like, oh, actually, that looks pretty steady state-ish. I'm going to comment this out. And see if we get a steady state now. Nope, still don't. So as stable as that looks,
For some reason it's not.
for some reason it doesn't like the steady state. I mean, this actually does. We only have 500 people, and so there's only so many places they can go.
It's odd.
And I would have thought that that would have a steady state, but we're not finding it in this, at least. Anyway, just like we did, like printed the model. And you may notice here something interesting. We have birth is nothing goes to susceptible. That makes sense. Zombification is nothing goes to zombies. And we have here susceptible to zombie or death is susceptible is the our beta like time susceptible. Basically, we have different rates here, beta and delta. And here we have zombification being beta and zeta. Basically, what this is doing, like since all of these reactions, quote unquote, have a single element in them, either like a single reactant, a single product, a single reactant, a single reactant, a single product, a single reactant, a single reactant. What they are doing in this model is like and instead of doing reactions, we're like basically just storing the DSDTs, like all these things. We're doing this in this sort of term instead of anything else. So let's confirm that. Here, I'm going to do a new, let's see here. I have a thing where oh yeah, this is it. That's not as useful as it could be.
No, I wouldn't try displaying differential equations.
Yeah. It's actually a little bit more, it's better than I thought it might be, because like we see how things are affecting other reactions, all these little dots, because they actually do show up in things. Oh yeah, we have like null outside. So yeah, that's actually not terrible. But it's probably, I've zoomed out too much. But if we wanted to make this better, we could, oh, this is what I was going to do here. So if I copy this all in, or in fact, I'm not going to worry about the units, I'll just do up to here and make this my new model. Let's make sure that I still get the old, what I used to here, right? All right. So if I wanted to actually like make this slightly better, I would have like zombification, and zombification is susceptible goes to zombie, and let's make that based on their model. Oh, rate. That's the slightly more complicated model. Is beta times S times Z. Beta times zombie. Right. And then if I want death, sure, death from a zombie is not that, is susceptible. Oh, Lord.
So what are you trying to do?
Turns
You're
out that
trying
like
to,
I
you're
was
trying
like,
to convert the ODE into individual reactions.
yeah. Is so death from zombie actually was like, oh no. Anyway, yeah. I was trying to convert it into individual reactions. Let's not like spend the time worrying about that right now. But you can imagine like changing the model to where it would actually go for, like, instead of being basically a set of ODEs to an actual reaction. You have susceptibles going to zombies, susceptibles going to removal, etc. Basically, you would take each of these reactions. You'd have 1, 2, 3, 4, and then birth is 5, and you would make it into a set of 5 reactions. And then you would actually be able to. And then actually, the other thing that might happen is that the steady state might work better. I think the reason why the steady state might be failing is because it has all these individual things. I could be wrong.
Same ODs.
Anyway. Yeah, same ODs. Anyway, that's that. Are there questions about like we're messing with things? All right. This is another, I'm going to zoom in on this too. So we have a site called biosimulations.org that has a bunch of, let's look at the actual models we have here. I think in a little bit this will populate with the actual list of models. Yeah, there we are. A bunch of the biomodels that have been reproduced by our team are like listed here. Like here we have, like a biomodels 10, biomodels 725, etc. And in fact, let's click on biomodels 10 here. So, oops. Biomodels 10 is another model that has it's fairly well known. It's a negative feedback model. It produces this oscillation. I can go to biomodels 10 directly. Nope, that's not what I meant. There. Bolodenko model, full text. And it's a map kinase cascade. And there's our ODEs. There's our more ODEs. And if we go down enough, we'll get to a figure. There we are. Yep. So this figure shows oscillation in this map kinase cascade. And in, where was I? At biosimulations. That figure was reproduced here, and I will show you how that happened. All right, we've installed this. I'm going to.
So can you show what you've installed?
What
have you installed?
This is called Biosim Client. Right. This is something that Jim's working on over at University of Connecticut to try to let Python users use the biosimulations mechanism. So if you want to run you can go here and actually run a simulation and upload a file to get stuff. Asks you to like upload a file and simulate it. There are a variety of different simulation tools that can run things. I happen to know that these are the 5 models of the 5 simulator tools that do ODEs. And if I tell it to run a biomodel stand, it will do that. I'm going to have to upload it. So I'm going to go to here, upload a file. I'm already in my directory because I did this earlier. Okay, great. And here it is. So with a relatively short program here, I can say like run this model on those simulators. And I'm going to show you what's in that model in a bit. But basically, actually, what's in that model are these files, and there's a lot of files here. But the one that's particularly important is this setml file. This setml file is instructions for what to do with your SBML model. Because if you just have an SBML model, you don't necessarily know how to create a figure from it. You just know, like, I could create a figure from it if I wanted to. Now, if I went to the curation tab, I might have to like read this, be like, figure 2A has been reproduced with Kaposi. Like, well, that's great. What did they do? And I might have to go to the paper and say like, oh, great, what does this figure say? And indeed, like, and here we go, like, for figure B, it's cooperative inhibition. This is n equals 2 and ki equals 18. Like there are a bunch of values that have been changed and stuff. And like, okay, so if I went through and made all those changes, then I might be able to reproduce this figure. But without doing that, I wouldn't be able to do that at all. But if someone else has already done that for you, like I did, then you can that file, those instructions are all in there in the setml file, and can tell you how to reproduce the figure. So then when it'll run it, sometimes it times out because it's actually like trying to do things in the background. If you've already run them in the background, then it'll find them and just pull them out for you. So this is all the different figures in all these different simulators. So here we have Amici producing those figures, Kaposi producing the figures, Tellurium producing those figures, V-Cell producing the figures. You can tell that it's not like literally the same because it looks different. And then Pisces doing the same thing. These are all very similar, obviously. It claims that, oh, interesting. It claims that Amici's and Pisces matched each other, and Kaposi and Tellurium matched each other, but all of them together did not. And then the V-Cell didn't match anything. Its closest score in infinity.
Could you touch on what's the reason for doing this?
The reason for doing this is because if you have published something, you want to be able to pick up, you want to be able to reproduce what someone else did, and you want to be able to move on and say, if you have a model and I want to pull someone else's model and use it and actually build on someone else's scientific results, I want to be able to make sure that I can actually do what you did in the past.
Yeah, but what's the point in running it across all these simulators?
And the point of running it across the simulators is to make sure that all the different simulators will actually do the same thing. And because SBML has different features and it has different like edge cases, and any given SBML model might run well on a handful of simulators, but might run poorly on a different one. There might be a case where like Tellurium assumes that you mean something in a particular SBML construct that someone else assumes means something else. Like Herbert and Frank, actually, we talked about, who's now maintaining Kaposi, several years ago, just went through the first like 200 biomodels or so, like all the biomodels that were there at the time, and just ran them all for 10 seconds on different simulators. And many of them matched like here, and many of them did not. And that sort of like pushed a bunch of people, especially simulator writers, to be like, oh, wait, why do we differ on how we produce like these figures? And everyone got together and everyone realized like, oh, we've been interpreting this construct slightly differently, or, oh, we need to do this more carefully. One of the things I realized when I was doing this is Tellurium, like I would run some biomodels and they would run fine on Coposi, and Tellurium they would fail basically. And eventually I worked out that Coposi was setting its tolerances, setting its absolute tolerance scaled by each individual species level, which basically means that if you have a model with a bunch of different with like different scales in it, so you have like one species that's 5 molar and a different species that's 6 millimolar, if you tell your simulator to use a single tolerance value for everything, either your tolerance value will be too large and your small and your 5 millimolar species will sort of get swamped by it, and then it can error out, or it can be too small and the very large one will like will try to be accurate to 27 decimal places and it just can't. So Coposi internally was scaling its absolute values, absolute tolerances by the initial value of all of the species. And when I did that in Tellurium then also like was able to properly run a bunch of different.
So what can you conclude from this run then that you got here?
So what I can conclude from this run is that these are all very similar to each other, basically. And
hold on, no, it says higher up though. One of the messages, it says no match for V-cell. Yes.
So let's look at what that means. One of the things that you can do is show dataset heat maps. And so let's scoot down, go up a little bit. So here we have all our simulators plotted against each other. So like along the diagonal is something plotted against itself, and we're just looking at overall sort of different scores. So the diagonal has all zeros, and the off diagonals have numbers. So here we have.
So what do the colors mean? The dark color means good, right?
Dark color means good, and then light color is more off. And so Tellurium is different from Amici, V-cell, and Pisces, but basically the same as Coposi. Coposi is different from Amici, and it's very close, but slightly different from V-cell and Pisces, and pretty close to Tellurium. And then Amici, V-cell, and Coposi, and Pisces all sort of match each other and are slightly off. Basically, one is your cutoff for whether or not we say things quote unquote match or not. So that's why it split things into two groups. It basically split these like Coposi and Tellurium into a group here, and then Amici and Pisces. And the reason why V-cell fell off is because V-cell has all these infinities here for plot. This is because of a dumb thing. Like when V-cell exports its data for plots specifically, it uses different labels for them than everyone else does. So the comparison tool here can't find the data like with a particular label because the label was slightly changed. So it's just different. So it's like, I can't find it. I have no idea what the match here. And it just says the difference is infinity.
So we just can't say anything then.
So you can't say anything about it, right? It's like, no, I couldn't match any data, so I'm going to put infinity here. So that's why we have like this group and this group, the 0.4 group and the Amici Pisces group.
It's difficult.
And apparently, like when it gets the labels right, it would include V-cell in that group. Say that again.
I can't figure out what the overall conclusion here is because the colors are all over the place.
They are a little different.
So yellow is bad,
right? But also, you know that like the fact that these are slightly over 1 means that they aren't terrible. If we changed our and the comparison was sort of an arbitrary number that we used. We said like this have to be accurate to within like, I don't know, 3 decimal places or something. If we had said that they needed to be accurate to 2 decimal places instead, then this basically it would change from 1.5 to 0.15 and everything would suddenly match again. But if this was like 5 million, then you would know like, oh, that's not the same at all.
Yeah, so we got some questions.
Yeah, sure.
What's the difference between the simulators?
The difference between the simulators they are literally different code. Sometimes the difference, like I know the difference between Tellurium and Copazi is that Tellurium uses a solver called CVODE, and Copazi uses a solver called LSODA.
Okay, and so one question then is follow on. Why are there multiple simulators instead of having just one unified one?
Yeah.
Yeah.
I mean, convenience and the interface. So the basic simulation at the base, if that was all you ever did with these models, then you would only need one simulator. But that's not all you do with these simulators. You interact with them in a certain way. Like Tellurium has this whole Python text-based interface. Copazi has a GUI that mostly uses tables.
But that's not a good reason, because you could have one unified simulator and just put on different interfaces.
That's also true. So yeah.
So what is the reason for not having a unified simulator?
Because they're all you're like putting me on the spot, but yes, I think it's basically.
I can help you out here if you want.
Yeah, I mean, one thing is just that like different simulators, different underlying simulator tools, like do different things and like make the approximations slightly differently.
We could make a unified simulator that includes all those.
Includes all of them.
Yeah.
All right. What do you think then?
So yeah. I think the reason is, I mean, partly it's historical, but today there's a push to be more systematic in relation to something called verification, i.e. to verify that a simulator is working correctly.
Yeah, that's also true.
And one way to do that is to have multiple simulators written by different authors, and to run the simulation across all the simulators to see how well they compare. And this is a way to verify the truth or non-truth of the simulators. So the problem with each author will probably add their own bugs to their code, whereas a unified simulator will have its own bugs, because no software is perfect, right? And there will be no way for us to figure out if it actually has those bugs. But by having multiple simulators that have probably non-overlapping bugs, we can identify the actual problems in specific simulators, because they may not run correctly compared to another simulator. So I think it's a good thing to have multiple simulators. It lets us verify across multiple simulators, and this is essentially what Lucien was doing. You know, you had in the top list, you had a list of all these simulators. The whole reason for running across those multiple simulators is to do a verification test.
Yeah.
And those of you who know something about the new idea of building digital twins, verification is an important aspect of the digital twin effort. And one way to do verification is to just run across multiple simulators. If they all give the right result, then you can be confident that that probably is the right result. But if they're all different, then you can be very suspicious and think there's something wrong here. And you might be thinking, well, why are there even bugs in the first place? Well, the problem is, well, it's written by humans. But we don't have any analytical solutions for these models. We do not actually know what the true solution is. I mean, for simple trivial models, you can, but for these kinds of models, we don't know, and we probably never will know. So we rely on this kind of thing to try to figure out what is the right solution. So that's one reason.
Yeah.
Somebody asked, how do you calculate the score? I think you mentioned that, right?
Yeah, this is basically it's the worst. It's the highest number in a number by number comparison of all the data across all the figures. Like the auto-generated report for task figure 2A, the autogen is like literally all the variables in the entire model all exported. So not only these things that were plotted, but everything else as well. And it just goes, it does there's a formula that you can use that I don't know off the top of my head, but it's like a NumPy compare or something, I think.
Okay.
So that's the other thing. Like if you wanted to be more like, if you wanted to delve into the weeds here and figure out like, okay, where did this 1.5 come from? It might come from, like the last point on a particular species that is starting to diverge from everything else. Or it might be like constant, like that 1.5 could show up all the time. Like it's always anything that oscillates, if you're slightly off, then all of your numbers are going to be, if your phase is slightly off, then everything is going to be off.
But I think the
yeah.
big issue is we
Mhm.
don't know, somebody looking at this doesn't know whether 1.5 is actually bad or not.
Right.
Maybe 100 is the point where it's bad, whereas 1.5 actually is not bad at all.
Yeah.
So
Like,
there's no
obviously,
way to
yeah.
judge that from that plot.
Basically, yeah. Like it gives
So
you,
it doesn't really
so
help.
why give it? But the other thing, it is at least a more objective number than looking at them and saying, oh, I think those are basically the same.
I
right?
don't know, because you don't know what it's telling you. You don't know
Yeah.
whether that 1.5 is actually bad or not.
Yeah. I mean, if it was, I mean, the fact that it's 1.5 means that it's right on the cusp. If it was
Well,
a few
who
thousand,
knows what the cusp is then?
yeah,
There is a
I
cusp.
suppose that's true. Yeah.
I mean, we don't know. I mean, unless somebody does know what the cusp is, right? Okay, well, that's something we should get back to on the Yukon people to ask.
Sure.
So somebody says, then should you use a specific biosimulator depending on what you want to simulate? Well, different simulators have different capabilities, so you will tend to choose one that matches the stuff you want to do. But most of these simulators do on the time course simulation, they're all very, very similar.
Yeah.
What's not simulated are any potential underlying bugs. That's what
Right.
this is used to spot. And it's a very good mechanism for authors to run their simulators through this to see how well they're doing, because this can be run on the entire biomodels database.
Yeah.
And you'll be able to pick up places where perhaps your simulator isn't doing so well as the others, and then you can investigate that and improve your simulator. So it's a way of helping the community improve the simulators, to get better and better. And then somebody says, is there an objective test best computational ODE solver? That is a good question. I'm not entirely sure about that. I mean, the modern theory in ODE solvers does have error estimates on the solutions, but again, we don't have analytical solutions for a lot of these problems, and so we don't actually know. I don't think so. That's a good question. Again, this is why you run across multiple simulators to see how well they're doing, and you just, if all the simulators give the same result, and then you can be confident that you've got the correct result.
Yeah. I was going to say, like, so this is like literally the work we've been doing recently is like we created a bunch of SetML files to say, like, do this experiment on these models, and then sent those instructions to all 5 simulators. And these were our results. Sometimes it wouldn't run on, so when it ran on all 5 simulators, for 265 of them, we got like officially replicated results on all 5. And then for another 42, we got like a group, like 4 of them all match each other. And then for 23, like 3 of them match each other. And then for 10, we didn't get anything that matched at all. Like all 5 of them were just different. So that's a really interesting group to be like, what is going on with these 10 models?
Yeah.
Do we just set our tolerance too high? Or too low? Like or do they actually match, or is everyone just going off in completely different directions with these models?
So there's a question. I think
Yeah.
if simulators use different ODE solvers, then choosing the simulator will depend on the characteristics of the ODE. Correct. That is true.
Yeah.
But these days, most simulators will use, high performance stiff integrators. I mean, let me go. 40 years ago, that might have been different. People would have used a Runge-Kutta 4th order, which is not appropriate for this kind of work.
Yeah.
These days, it's better. Most of the popular simulators use good integrators, so it's less of an issue. So does running the biosim client help see my own bugs in my model? No, it's bugs in the simulator. Bugs in the model, you're on your own.
I mean, it's also true that if you have a bad model, or if you have a very like fragile model, like you might be running on Copasi or something, and you may find something that gives you a result on Copasi, and then you try to run it on everything else and it just fails. And something weird like let your model get results on Copasi.
It might be, yeah. But primarily it's to check the simulators.
Yeah. But you also want to make sure that your model will actually run on. I have run across several models in biomodels database where like they ran it on Copasi, they like reproduced the figure, like great, they published. And then I try to run it on anything else, and it just doesn't work at all.
Yeah.
And it's usually because of something weird is going on with the model itself, like a posi happened to ignore. So there's bugs, and then there's other bugs, right? Basically, it's a bug in Coposi that didn't care about some problem, and then for the other simulators, they did care about the problem and they noticed it.
Okay, so there's another question.
Yeah.
I had a few. Okay, what models don't currently have analytical solutions? 99% of them. All these models are nonlinear, and in general, there are no analytical solutions to nonlinear models. I mean, in other domains like electrical engineering, they will generally use linear models if they can, and then they do have analytical solutions. But even then, that's not always the case. In biology, almost always the models are nonlinear, and there are no analytical solutions.
Is
So,
one addendum to that is
Yeah.
that a lot of times what people will do to test their, in general, insolvable nonlinear models is they'll have edge cases that they can test. They can solve analytically. Maybe it approximates a linear model. And so that's another kind of test, but it's not the same thing as what was just described here.
there's another question. Would you call this robustness of the model if it can run on all simulators? That I don't know.
I kind of think so. Like when the simulators are not buggy themselves and your
Yeah.
model can run on all of them, that means your model is robust.
Yeah, but what do you mean by robust though?
I mean, on a practical level, it means that anyone who uses your model will get it to run and it will do the right thing, right? No matter.
I mean, I guess it means the model hasn't got any weird stuff in it that's non-biological or non-physical.
Yeah.
That would cause problems.
Or like hypersensitive to
Yeah,
small,
hypersensitive. Yeah.
to initial conditions.
But I think primarily it's a test for the simulators. And this is something, we definitely need. I mean, as these models will start to migrate to the clinic, some models will end up in the clinic. You want to be really sure that the models, are operating as you expect. So, I mean, there's biological robustness that's different. I guess that's why I asked. Yeah, I mean, if your model is hypersensitive, that is a problem with the model, I think. Most biological systems are not hypersensitive. If they were, I'd be falling over the minute I, stood up. So yeah, most systems are not hypersensitive, and that's an evolutionary thing. And if your model is hypersensitive, that probably suggests the model is probably not quite right. So this is a general direction that some of the community are moving in to check for verification. The other thing is to check whether your model is valid, i.e. does it match, experimental data? And the other thing is how much uncertainty is there in the model predictions? I mean, if you have a fantastic model, it's verified, validated, but the predictions are so uncertain, then that's not particularly useful either. So there are these areas that various people are working on to try to improve models. This is because models, there's a push to move models into the clinic, into areas, human health, and these things then become more important. As an academic, these things are perhaps less of a priority, but certainly in real-world applications, these aspects become a priority.
Oh.
Have you got much more? Or
just a little bit here. Okay. I wanted to just show that if you run Tellurium, there is the other thing was, like, I just wanted to show you, like, when you're looking at one of these models, up here, there's a download button that says download omex format of this model. And that gives you these the omex file that I've been showing you, which is basically just a zip. It is a zip of all these files. It needs this sort of magic file called a manifest in there, which Biomodels now has, and which just sort of tells a omex interpreter what different things are. So that's basically where this biomodels10.omex comes from. Is if you were to go here and click download, you would get it. And I was hoping to do that with some other things. And then Tellurium has a function called execute combine archive that's completely different code than even here. Like when biosimulations ask Tellurium to run it, it interprets the SetML itself, and this is a different interpretation of SetML. So again, it's sort of like a separate to make sure that everyone's interpretation is the same. It can define bugs, and here we have figure 1 and figure 2 from Tellurium itself. So I've uploaded the actual SetML file and the XML file. The SetML file is, again, like SBML, not useful to look at directly. But if you use a library that Kiri and I wrote called PhrasedML, you can convert your model from SetML to a text version, and this is what it shows you. So this is a slightly easier way to understand what's going on in the SetML. So we have Kolodenko, which is just load that model. Kolodenko B, it's load the Kolodenko model and then make all these changes. And if you remember, I told you that in the figure, not this one. Oh, in the other figure. No, I'm wondering where it was. Was it here? Yes. Here we go. Like here we have a list of changes, right? So here, that whole thing is, those are all those changes. This equals KK9 is 100, KK10 is 100. Interestingly though, and this is something that another student in our lab figured out, Jen, you also have to change these values. You have to change the initial value of map K, map KP, and map KPP. Otherwise, it doesn't actually match the figure. If you don't make those changes, you do see this oscillation, but it doesn't start in the same place, and it does slightly different things. You get the basic idea of the figure, but it was not the actual figure. You see this like starts at 275 or something, and here, so map K in this figure starts at like 270-ish, and then this model map K also starts there, but other things don't. That was around 0, map KP. I don't remember. Anyway, but we had to make those. We had to make those changes. Oh, you're 260, 35, and 15, because otherwise they just weren't actually looking the same. The simulations were slightly different. The first figure was 0 to 9,000 seconds, and the second one was to 1,200. And if you look, like, time minutes is 200 on this one and only 150 in this one. The algorithm this just means it's a uniform time course. And then the time was in seconds, so we divided by 60 to get minutes, and then we plotted them versus BAPK. And those are the two plots here. And then the reports are like CSV files of the results. So with looking at this, you could write your own program to do the same thing. You would know, like, oh, okay, I have to simulate from 0 to 9,000 with and then I have to simulate from 0 to 1,200, and I have to make these particular changes. I would just like take that list and put them in as changes. If you wanted to look at the model itself, you could load Antimony. You can use directly. It's usually nice to use Tellurium to sort of do the conversion, but Antimony that's how you do a conversion directly in Antimony. And then you can sort of look at what the model is like. So if you wanted to sort of get more into the details, like what's actually going on, you start looking at the Antimony version.
Lucian, I think that SetML is much more featureful than PhrasedML. Could you give folks a feeling for, where the limitations of this conversion from SetML to PhrasedML?
So there are things like the fact that this has a solid line and a dotted line, just like the original figure. Where is the here? So in the original figure, we have a solid line, a dotted line, and we did that in this. And that's not something that PhrasedML will understands yet. Is the difference like the colors of lines with the fact that it's dotted or something. You can do repeated tasks in both SetML and PhrasedML. I mean, the main problem with SetML right now is that it's hard to create. Like, if you're going on and like running a simulation, you're going to run your simulation like we did, like this, right? You're going to say like, we're going to say like, set some values and simulate and then plot. And if I want to translate that to, because this is a perfectly reasonable thing to store in SetML, like set a couple of values, simulate this, and show me the results. And what we and that's what's stored in SetML. But right now, there's no easy way to like take this program and just say like make this into SetML. So I would say like the main limitation of SetML is just like trying to create it in the first place. And so the features of it are almost immaterial. It's like someone used it to do a thing, and hopefully PhrasedML will like let you see the basic things that are happening in there. Coposi will export to SetML at least a figure. If they like, it will. If you in Coposi you have a figure, you can export it. It won't do these sort of like change this to this and this other to the other, because it'll just export the version of the sbml file that goes with that particular figure. So it would export like a new model with zombie at 0 and p at 0. Question: does the runner provide methods for global and local sensitivity analysis? It does, right?
No, it doesn't.
Oh, it doesn't? What does it do?
Only local.
Only local. Okay.
You'd have to write your own Python script, and there's probably some packages you could use to do global sensitivity analysis. So I mean, that's a good question, actually. Yeah, this is something we could. I'm sure there's a package you could use to do these global sensitivity analysis,
yeah.
and just plug in the simulator, and it would do it. So
yeah. Joe, is there something in particular that you were thinking of?
Well, what I was particularly thinking of it in terms of helping people, I'm a big fan of PhrasedML, the format, and I love the way it presents things in an interpretable way. But if somebody goes to biomodels, downloads the OMEX, wants to look at the SetML, I was just wondering about the limitations of what they'll see if they're looking at it in PhrasedML. Because there potentially are features in SetML that are being used that I don't know if PhrasedML would fail if you had different different dash lines, or it just will ignore that and show you just the plots without that, or what will happen?
What will happen? I mean, actually, like if we look at this SetML file, in fact, here we go, right? It indeed has these styles, a solid line, a dash line, and you just don't see that in the PhrasedML, so it just ignored them.
Okay, so it ignores the features. I mean, you still have the benefit of sort of the summary of what this is, because the first order question is, what did somebody do? Right. That's the first order question.
And if we had a little bit more time, I would like pull up a random PhrasedML, random SetML, look at it in SetML, in PhrasedML, and then write a program using Tellurium to do that. Right. So I would like actually say like load this, set those values, simulate from 0 to 12,000, right? And then and see what we get. I could do that, but we're over my time officially, but
yeah.
Okay.
So we are. So and we had some discussion on the chat. Is there any other? So we are, in theory, we have some time for discussion, but we're a little bit over time. But if anybody's got any questions or something like they'd like to discuss, now's your chance. I know we've had a lot of commentary in the chat, which is good.
Yeah.
If there's anything else, otherwise we can move on to.
Yeah, and thank you all for all your questions. That was great.
Parameter fitting theory, and then we'll have a break. Okay. Unless you want to break now and then come back. I wonder what the.
No one's going to say anything.
Because we've been going for an hour and a half. Hands up.
You want to
break
do
now?
Yeah. Why don't we just sit up, yeah, like 5 minutes, something short, just
Yeah,
so that
okay.
people have blood flow to their bodies.
Yeah. Okay, we got one hand. There you are. The vote is in.
Okay, right. The vote is in.
It's a
Sheila,
yes.
you speak for
It's
everyone.
unanimous,
We're doing a
right,
break. Oh,
okay.
there we
another
go. A
one.
couple
Right,
people
yeah.
Two.
there.
It's double unanimous.
Yeah.
Okay, fine. Why don't we do like 5 minutes just to get some blood
Okay,
flow?
time
Sorry.
to get a cup of tea. Okay, great.
Perfect.
Folder itself.
Oh, okay. Yeah, I can do that. So this is our day 2 folder. This is
Yeah.
what it is. Okay. All right. So see where I am here. Go back over here. All these controls are getting in the way. Okay, so the folder itself is right here. I will chat that.
Okay,
Okay.
got it.
Okay, good.
Right. No, that's odd. It's the same folder. That's the wrong one.
No, I picked up the wrong. So I guess I went.
Oh, hold on, I see the Gemini one now. Maybe this.
Yeah, no, I think. Yeah, no, this should be the right one because it
Oh,
has the
okay.
2 in front. For the.
Yeah. Got it.
Okay. All right.
Yeah, that's fine.
Okay. So all right. Okay, we're
Yeah,
good. I
that's
was
fine.
going to.
That works.
All right. Okay. All right. All right. Should I go ahead and start?
Yep. Thanks. Yep.
Okay, great. So I'm Joe Hellerstein. I'm at the eScience Institute, University of Washington, established about, about 15 years ago. If you remember way back, data science used to be a big thing, and now it's AI. So, times change, but our name stays the same. And actually, eScience predates that. It was for basically computation-based science was the idea. I think the E was for electronic. Anyway, I'm going to be talking about parameter fitting. My background is computer science. I have a PhD in computer science. I did a lot of stuff in sort of the early days of distributed systems. It was all about scaling. We still have a lot of that theme today, I think, that's going on with AI. You see the growth of the number of parameters, for example, in models and the amount of text that's being ingested. So computation figures prominently into many of these concerns. You'll see it in parameter fitting, and also later on when Herbert and I talk about AI for modeling. And a lot of what this talk is about, it's about motivating why we want to do parameter fitting. And it's an essential part of the field, actually, with any computational science. Being able to estimate your parameter values is critical. The other part about this, which I think folks have less of a feeling for, especially if you don't have a formal computer science background, is what are the limits of doing this kind of work? It turns out that very quickly, especially in biology, you just don't have enough compute to do this even for relatively modest sized models. And so there are a lot of assumptions or limitations that have to be, and qualifications you have to put on what how you obtain parameter values for your models. Okay, so sort of an overview perspective. Let me go on and give you some of the content. So this is my sort of meme here about you start on some of these problems. It looks like a relatively simple problem. Before you know it, you find yourself in this sort of computational pit where the amount of work involved is much more than what you thought it would be. So, okay, so what is parameter fitting? I think you've gotten some introduction to this. This is one of my favorite models, the Jenner Wolf model from 2000 about glycolytic oscillations. And I think you've seen this in a few different lectures. I think I know Lucian provided some of this and sort of a summary
I
here
think just
about
that
what's.
one this morning. So, but yeah,
Exactly. I saw you when you were doing the reproducibility.
exactly.
So if you look at this model, just even a little bit, you say that you see what it depends on a bunch of these parameters, and where the parameters come in is going to be, well, here's the model itself. It's a relatively small model for the amount of complexity it has. And a lot of the complexity, of course, comes in from when we talked about earlier that these are nonlinear models. It's, typically there's more than one reactant, which means there are interactions between reactants, like over here. And then the actual rate laws involved are complicated. This one right down here for J4 is a good one. So everything after the semicolon is the rate law. And you see, like J4 underscore KG and J4 underscore KP, these are all parameters that have to come from somewhere. And you see a subtraction here, and then there's a division. So the subtraction could be linear, but the multiplication of, you get multiply in here, some of the floating species, their concentration, so that's nonlinear. And then you've got a division over here. Well, these are constants, so that doesn't really matter. But multiplying the floating species together definitely is going to be a problem. So if you look at that and you go through, and actually if you go a little bit further here, I've highlighted here all the parameters here. Typically in even modest-sized models, and I would say this is modest size, it's not trivial. But it's not, we have many models that are, 50, 60, 80 reactions. You'll find at least on the order of, 1 to 2 parameter per reaction. I mean, that's pretty common. So that means even with modest-sized models, we're probably talking, in this case, we've got 16 parameters, 20, 30 parameters. That's not uncommon. Some of the parameters you would hope you could estimate by looking at biological data. And there are published sources for this. I mean, biomodels will give you some of this. There are other sources. Brenda, I believe, is another source that you can get for some of this. The problem is that these parameters, their estimated values come from non-physiological experiments. Somebody did it in a test tube. It wasn't under physiological conditions. So, you sort of wonder, I mean, it might give you an initial hint, but, you don't know for sure. So that's one challenge, is we really don't have good estimates for many of these things, at least not how it works for, the particular physiological context in which you're trying to do the estimates. The second consideration, and this is more of a mathematical and computational concern, is if you look at the values of the parameters that were used in this model. So I'm showing here the values that this model was published with. Look at the range and look at the variation in the scales here. I mean, this is a constant of 1, this is 4, so close to unity. And then we get things that are like 57,000, 76,000. Yeah, this is such a wide range. So now there's this term that you've probably heard before, very common in computer science, called search space. That's basically, if you think of, if I was looking for one parameter like J1, K1, I'd have this one-dimensional search space. But I've got 16 parameters, so I've got a 16-dimensional search space. And the size where I have to look in that space is really complicated, because here I want to look close to 0, and here I want to look at close to 100,000. And you'll see some parameters that are fractions of 1. So the search what the term is search space is really huge, and it's continuous. And so it's a very difficult problem to come up with something accurate. Let me mention one other consideration that I'm not going to go into a lot of detail here because of some limitations on time, but there's a concept of what's called identifiability. And that is, do you even have the data so you can figure out what this parameter is? I mean, for example, if what I was measuring was just glucose and I guess let's say fructose 1,6-bisphosphate. What I want to do is be able to see how well these predictions compare with the actual measured concentrations of these two metabolites. But what about glycerate, 3-phosphate, or acetaldehyde, or NADH? If I don't have data for them, then well, I could probably figure out a lot of values of the parameters that'll work. So that's what's called identifiability, and it's partly a data issue. It's also a modeling issue. There's some things that just the structure of the model makes it so you can't identify it. So I'm not going to go into detail about that, but that's definitely a concern as well with this problem with parameter estimation. Just be limits to what you can do with the data you have available. But for right now, let's assume we have all the data we could possibly need. And I'm going to focus more on the computational side for right now. And this issue with the number of different parameters and their huge range of, the scales of the values of the parameters. And, if I don't have a lot of insight about what those scales are, it's a challenge. So here's some of the basics. And what I'll do is I'll sort of set up the problem in a very general way about what it is, what is the task at hand to be able to do this and sort of the core concepts involved. So what we want to do is find values of parameters so that given some observational data, we can set those parameters to values so that our model reproduces the measured values. So if that all makes sense. So we've got, this is what's called training data in AI. I mean, it's really analogous, totally analogous to what goes on with training a neural network, where you start out with your training data, and that's the way you estimate that. And these are also parameters of a model. It's just a neural network model. And what you're trying to do is use that training to come up with good values of parameters so that then when you have test data, you do a good job with predicting that test data. That's exactly what we're doing here, the same idea. Okay, so in contrast to a lot of the AI stuff, the parameter fitting area, it's a more modest problem. I mean, the AI problem is a huge problem, but this is a more modest problem. And it's also been studied in a lot more formal way. And so there's some additional concepts that people don't necessarily get exposed to as they would in the AI world. So one of the core concepts here, which we'll use a lot, we'll refer to a lot, is something called the residuals. It's probably one of the most central concept in practical statistics. And what it is, it's a really simple idea. It's the difference between the observed value, which you got from the laboratory, and what your model predicts. That's the residuals. And if the residuals are close to zero, you've done a great job. Your model is spot on. And if your residuals, are large in absolute magnitude, obviously you've missed the boat. And then depending on the sign of the residuals, it tells you something. So if the sign is positive, then what happens is you're tending to underestimate the observed values. If the sign is negative, you're tending to overestimate. So the residuals are sort of the key idea here. So here's a generic algorithm for parameter fitting. And from this, we'll get into what makes this so hard. So the inputs to this is we have a model. And we've been looking at a lot of models here. We're going to focus, just think of like an antimony model. We've got the parameters to estimate. We've got a whole, gave examples of that with the General Wolf model. You've seen this in other presentations that Herbert has done, certainly. And the third thing, which is sort of new to our discussion, is we're assuming that we have some observed values, some laboratory data of some sort. And typically, laboratory data is we don't have a lot of it. I mean, even if we have a lot of values, it may be like 20 observations of 10,000 genes or 5,000 genes. So it's sort of like very broad in terms of the number of things we're measuring, but we don't have many separate individual samples. It's just that each sample has, 10,000 values because it's 10,000 genes for, the number of transcripts we found. So we've got observed values. Then that's something new that we're bringing to this because we want to try and figure out good values for the parameters to estimate. So that's our input. And what we're going to come up with are values of the parameters. So some number that should be associated with each parameter. Okay. So here are the steps. We'll go through this. Okay. So this is if you haven't heard the term before, this is what we call pseudocode. Pseudocode is it's formal in the sense that you're giving a step-by-step procedure. I mean, the olden days we used to draw boxes. We have flowcharts. So this is sort of like a textual version of a flowchart. And actually, a lot of times people, software engineers will do is they'll start out with pseudocode and then gradually replace it by, actual executable statements. So this is sort of somewhere in between. So do this until you get a good estimate. So what does good mean? I mean, that's going to be subjective. You have to figure that out. Or it runs too long. And again, what does run too long mean? You know, how much CPU can I pay for on Amazon or Azure? Okay, so here's the first concept here, this notion of a setting. So what you do is you take a new assignment of values to for the parameters. So we've got all these parameters like J1, K1, and K4, J3, or J3, K4, whatever it is. And what we're going to do is, in order to run the simulation, all these parameters have to be assigned a value. And we're going to call those the settings of the the parameters to a specific real, typically it's going to be a real number. Okay, now that we have the settings assigned, we can actually run the model. So now we got a simulation result. And here's where the residuals come in. We subtract the observed values that we got from, these were the an input, the experimental data, and we subtract out the values of the simulation, and that difference is the residuals. And so then one way of assessing how good we are, I mentioned if they're close to zero, well, since we have negative values and positive values, we have to take care of that. You can look at the sum of the absolute values residuals. Typically, you look at the sum of the squares so that the things don't deviate too much. And if that sum of squares is pretty small, then what you're going to do, if it's smaller than the previous settings, then what you're going to do is you're going to replace, you're going to say, okay, I'm getting closer to what I'm looking for. In other words, the absolute sum of the squares of the residuals get small, then that's a better choice of setting. So now I've got a new update for my parameter estimates. And if the sum of the squares of the residuals are really small, I may say, aha, I've hit gold. I'm good. These are my parameter estimates, and that's what I return. So I keep on doing this loop until I get down to here. So one question, of course, is, well, what if I never get very small? I'm just guessing wrong all the time. And that's where this is our escape hatch. We exceed the runtime limit. So this root loop does terminate. It just may take some time. So, okay, fine. That looks pretty obvious. I think most people I know when I present this, I say, yeah, in classes especially. So yeah, okay, fine. So you said this is a hard problem. What's so hard about this? This is the hard part here. You can have a lot. How do you figure out what those new parameters are to estimate? Especially since there are so many different possibilities. And that's sort of the focus of what we're going on here. That's sort of the search part of this. Like, how do you figure that out? And there's one special case, which I'll talk about in just a couple of slides, where this is pretty obvious to figure out, and it works really well, and the algorithm runs fast. The problem is that it is a special case, and it doesn't work for most models. Okay, so what have we got here in terms of concerns about this whole parameter fitting, project exercise? What's sort of hard about this? Okay, so we're fitting a large number of parameters. I mentioned before, like, even this Jenna Wolf model, 16 parameters, typically to a relatively small data set. And by data set, I mean the number of distinct samples. So I gave the example of you've got 25 measurements of 5,000 genes. It's not the 5,000 that you're concerned about, because that's just, it's a big vector of data. It's the 25 samples. You only have 25 samples. And the problem here, this is typically attributed to John von Neumann, is that the more parameters you have, and you've probably heard this many times, I mean, if I have a large number of parameters, I can fit almost anything. So, we'll actually come back to this later on. There's a lot of analogies between this, or connections between this lecture and the AI lecture. And that is, well, wow, what about these models I read about that, gee, this is a 7 billion parameter model. This is a 500 billion parameter model. Doesn't that mean we have a lot of parameters in these AI models? How does this even work? And the answer is, yeah, it's sort of interesting. Nobody really understands. I mean, there are theories, but nobody really understands why that works. It shouldn't, in some sense, but we'll get back to that. We can talk about that more later on. But the practical fact is, for parameter fitting, and and the way, we're going about this for this, specific, kind of problem, this is a huge concern that we essentially have overfitted the model. And so, we can find parameters that will make it fit the experimental data, but it doesn't necessarily mean we've attributed, we've got some truth associated for it. So that's an important concern to keep in mind. And it's a sort of a limit of the whole exercise of parameter fitting. Okay, so the observation here, he talks about, 4 parameters or 5 parameters, and typically we're talking about tens of parameters. Okay, a second concern, and this is one which folks, I see I've got a whole bunch of questions here. Herbert, have you or Lucian addressed these, or should I look at them? I just wanted to make sure I'm not continuing to talk where people have fundamental questions.
Oh, someone was just talking about like searching like exponential spaces instead of like linear space, I think.
Okay,
Yeah, like,
all right.
If you don't know if your number is 1 or 10,000, then like searching log space is a lot more efficient.
Okay, fine.
Than
Yes,
searching
right.
linear space. So yeah.
Yeah, and that's a fair question. Right, and there's of course, then all you've done, you've translated the problem so that now the difference between 2 numbers has a very different semantics, because now I'm in log units rather than I don't, and we can, that's a side conversation for right now. I'd be happy to have that conversation. I think you may have just transformed the problem rather than solved it, but we'll see.
Well, it makes it easier to like if indeed the problem like if indeed the number might be 10,000 or it might be 0.1,
right.
The only way to tell the difference is to like search linear space for that. You're not going to, if you do a linear like 0 to 10,000, you're never going to search those like effectively those 0 to 0.1 values.
Yeah, we could go another right.
Right.
Okay, so let me give you just a simple insight into the computational side of things, because this may be something that many folks, again, unless you've had formal background in computer science, may be a little bit less familiar with. So here's the setup. We're going to look at the effect of the number of parameters in the model and the number of different values we're considering for those parameters. Now, in reality, of course, these parameters are continuous valued. And so, it's an infinite number of possible values, but we're going to simplify the problem, say we're just going to look for a subset of those particular values. Because if that subset of particular values, if that search is hard, then obviously the continuous search is even harder. And because going back to the log thing, and log is a great transformation, we're going to use the evaluation of the time it takes. We're going to assume that each simulation, so once I've assigned a set of values to parameters, and I run a simulation, like in that algorithm I introduced before, we're going to see that it takes a microsecond, just a round number. It's a far too optimistic, but it's a round number, and so we'll use that. And what we're looking at is as we vary the number of parameters and the number of values that we can assign to parameters, distinct values assigned to parameters, we're going to come up with a time, just doing the straight combinatoric evaluations of this. And we're going to report that time in units of log 10 of the number of hours it took. So that's what's going on here, just to give you a feeling for the units. So we're looking at log 10 of hours. So a second is negative because it's less than an hour. An hour is 0 because that's unit 1. A day is 1.3, going up to the age of the universe. And this is certainly where log gives us a great way to simplify what the numbers are. So if your calculation is going to take the current age of the universe, which was like 14 billion years, something like that, log base 10 of that in hours is 14. Okay, so let's go through and see what we've got here. So I'm considering up to 64 parameters. The Jenner Wolf model was around 16. This is the number of different values I can assign to each parameter. So if I'm considering for each parameter 2 values, I'm here. You know, if I'm considering 64 values, I'm down here. I mean, realistically, you know, you probably examine a number of values across the continuous set available, probably something more in here. So we see, you know, it's the trend is very clear. With the more parameters and the more parameters and more values, you know, it takes more time. What is disturbing is the amount of time as we get into a region in which is pretty typical for you know, kinetic models today. So Jenna Wolf, we're talking about 16 parameters. You know, and let's say we're just talking about, I'm going to consider just 8 values for each parameter. Well, I see 4.9 over here. That's somewhere probably like 20 years or so. It's between a year and a century. If I'm talking about something that's a slightly bigger model, like 32 parameters and maybe, you know, maybe just 16 values for each parameter, I'm twice the age of the universe. So, I mean, obviously, this is what's called exhaustive search. We consider everything in combination. Clearly, that fails, you know, for what we need to do. And the practical matter is, since this is an easier problem than our real problem is with continuous values. We understand that this is a rough approximation to even the computational solution that we want to get. So you just have to bear that in mind whenever you look at the results of your parameter fit and say, oh, I've got it now. I'm going to go forward and use this. You know, you've got something that's a very rough approximation to reality. Okay. So I promised you before that I would show you that there actually are cases in which this problem can be solved very simply. It's just that what we have doesn't apply to that case. But it's a good thing to understand in terms of how you're, you know, this general nature of this fitting problem. There's a notion of what's called a fitting surface. So this is of course in a high dimensional space. So we've got these 16 parameters we're looking at, and our search space is 16 dimensional. Okay, I'm going to add one more dimension to that. This is going to be the 17th dimension. And the 17th dimension is going to be the value of that. You know, remember we talked about the residuals, a way of looking at how good something is. So if I search all combinations of these 16 parameters, my 17th dimension is going to be the sum of squares of the residuals for that particular point in the 16 dimension space. That makes sense? The 16 dimension space, I'm going to come up with, you know, for each point in that space, you know, so each a setting for a the 16 parameters, I'm going to come up with a residual sum of squares. So that's my fitting surface. So let's take a look at the fitting surface. We're going to use a really simple model. So our fitting surface is a low enough dimension we can do something with. So here's our model. We've got this, you know, floating species X over here. And what we're doing, we've got an input X0, we've got an output X1, X is in between there. Here's our simple differential equation. These are the capital letters are fixed values. So I want to look at the change in I'm going to look at the concentration of X. I've got the differential equation over here. This is a linear differential equation, so it's really simple. And I've got 2 parameters. So instead of being in dimension 16, I'm in dimension 2, which means now I can plot some things. So I can do a 3-dimensional plot and actually look at the fitting surface for this very simple model. So if I do that, you know, here's my space is this, you know, the horizontal axis is K1, the vertical axis is K2. Those are my 2 parameters. I did a simulation where the true value is K1 equals 1 and K2 equals 2. So this is where, I know since that's the true value, that's where my residual sum of squares will be 0. Because that's the true value for this and this space. If you look at the shading over here, my 3rd dimension is represented as a heat map. And these are the residual sum of squares. And they go from 0, which is, if you see there, that's really light. I sort of wrote over it with the red dot. And as it moves away, it gets darker. So it gets worse. That means that the residual sum of squares are higher. Okay, so you can actually zoom in on this a little bit. So you see the scale changed here, and everything that's white over here, I didn't analyze. So just ignore. That's as if it doesn't exist. But you can see now I've rescaled it, so you can see the dark and the light, and you see that along this line over here, it gets very light. Okay, and right there, it leads to there. So actually, this particular fitting surface, this third dimension, the color thing, has a very interesting characteristic in that if I have a trivial algorithm here, which says I'm going to move from dark to light, that's my algorithm. I'm just going to move from dark to light. That's called gradient descent. And I think Herbert will probably talk some more about this shortly with solving these problems. So if I do that gradient descent, I will actually end up at that red dot. And that is very cool because then I have my structure of my fitting surface is such that I can solve this problem very efficiently. So, okay, so you may be asking at this point, yeah, but okay, why did I spend the last 25 minutes getting to this point if you say it's an easy solution? And the answer has got to be that it's not really an easy solution. The problem is that for practical models, this is not your fitting surface. Your fitting surface, like for this General Wolf model, is something like this. Okay, well, okay, now it becomes a little bit harder. Again, it's the same idea. I'm just doing 2 of the 16 parameters. So, here's my fitting surface, 2-dimensional space. I look at these 2 parameters, and I want to somehow start in some random part of this space and get to this red dot. That's the true value. Well, I've got all these ridges, and what the term is local minima. So I can get on one of these ridges and get stuck. Only if I'm pretty close to this red dot could I use that gradient descent approach. So, and that's the problem we face. And so you can naturally see there are a lot of different ways you might approach this. I mean, maybe I could have a smarter search algorithm that could actually come from here and doesn't use just gradient descent, sort of pops around or something. Another thing which is really easy to do is you could do multiple restarts, just sort of populate this maybe in like almost a grid approach and do gradient descent within each grid. But typically what's going to happen, for especially with 60-dimensional space, is you'll end up with a lot of local minima. And so once again, you may have many solutions that sort of work, but you haven't found the true value. Okay. So what are we doing here in terms of the factors affecting the complexity of the fitting? And this is sort of the summary here. So we've got the fitting surface. Is it convex? Okay, well, if it's convex, that's what this is called. This is called a convex surface. That's the term that's used over here where gradient descent works. Okay, if it's convex, problem over. It probably means that you have something you could have solved analytically anyway, but so that's convex. Otherwise, you're gonna have a lot of local minima, and so that's a problem. You got the number of parameters that so now if you've got one of these spaces, then we're something that looks more like an exhaustive search. You can't be take advantage of gradients. And now it depends on the number of parameters, I'm considering, the starting point, my observational data, what did I measure, that type of stuff. And then I mentioned before the identifiability problem. Okay, so that's sort of my overview. Give you a feeling about what this is, why we're doing it, and why it's hard. Okay, let me pause at this point. How am I doing on time? I didn't keep good track.
It's 11:15.
Okay, I don't know how that fits into the schedule.
I don't know how that fits either, but
okay, fine. Okay,
it's maybe been half an hour, I guess.
All right, so I've been okay, fine. I was gonna pause here to see if there are questions. And I don't know if this helps in terms of our timing. I don't see, at least on my chat, I don't see anything new. Were there anything else pop up that folks had questions about? All right. Okay. All right. Well, then let me stop at this point.
There's one more question. Are some of the local minima biologically relevant?
Are some of the local minima relevant? That's an interesting question. I mean, like, did we discover something interesting even though it's a local minima? I don't have a good answer to that. It's possible. It's possible that may have some significance. It's not something that I'd particularly investigate. But interesting question. Other questions?
Yeah, I mean, I guess if you've done some synthetic searches, you have like create a model, you create data from the model given particular values, and then like try to find those values again. Do you find values that match the results?
Oh, from the
Anyway.
previous search? Yeah,
Yeah.
right.
Or that
That's
are better
right.
than the, I don't know. Yeah.
Oh, okay. So this gets into a little more detail that Herbert may cover, but there's a question. So one of the ways you can address the concerns about the fact that you most likely are just finding local minima is how often do you find different local minima? You know, and there are a variety of techniques. This is uncertainty quantification is the broad term. And there's bootstrapping, if you've heard of, folks have heard of that technique. That's one approach. There are other approaches to doing this as well. That's one way to try and quantify the extent to which you are certain about what you found, because you may not be able to find the right an answer that really fits, but at least you can say, look, this lies within a small range given the constraints of my data and my model. So may have answered too much. Other questions? Okay, well then I'll pass on to Herbert or the agenda.
Yeah, okay. Yeah, okay, great. Okay, so I just start. So what we're going to try now. Let me just share my screen. So this is what I'm going to thought I'd do here is actually do a live. It's very dangerous to do anything live. But trying to do a live. We're going to write a program that'll fit a model. Okay, so that's the objective, is to write a Python program that will fit a simple model to some experimental data. Now, the experimental data will be something we'll create, okay? So we'll create the experimental data in the Python script, and then we'll define a model, and then we'll try and fit that model to the quote-unquote experimental data. And we can, because we can create the experimental data ourselves, we can add some noise to that data to sort of mimic what real experimental data might look like. Excuse me. Okay, so I think is this ready to go? Code. Okay, let me check if I got Tellurium imported. Oops. Now, Tellurium doesn't have, oops, got the usual. Okay, let's try that. Okay, now it's happy. Now, Tellurium doesn't have any parameter fitting built in. The reason for that is, I mean, we did think about it at one time. The problem is it's a sort of moving field. It continues to advance, and that would mean, and there are people who produce material which is really good, and we may not be able to do that as well as that other people can do. And so instead, we sort of decided, let's show how to use Roadrunner with existing fitting software. Okay, so you can pick your own favorite fitting algorithms, and then tie Roadrunner into that, or Tellurium into that. Okay, and especially in the recent years where the emphasis has been more on Bayesian approaches. I'm not sure if I'm a big fan of it myself, but Bayesian approaches where it tries to take into account, it explicitly takes into account the fact that there's uncertainties in your data, and then it propagates that using these Monte Carlo techniques to propagate that data into your fitted estimates. I mean, one issue with those is they're very slow, and so people have been trying to make them faster and faster. And they are a little bit faster now, but then you lose accuracy. But we decided not to do that because we will let other people use whatever fitting algorithms they want, whether they want to use Bayesian, non-Bayesian, or whatever it is. Okay, and the packages keep on advancing, and you can, and that means you can exploit the latest developments. rather than us implementing some fitting methods, which will probably, go out of date, and they won't be maintained as well, perhaps, because we have to maintain the RoadRunner itself. And so the choice then was made to not support fitting explicitly, but to let people hook up RoadRunner to a fitting package. And so that's what I'm going to show you how to do. And it turns out to be not that difficult, okay? And the fitting package we're going to use, the one I've used a lot, but there are others, is lmfit. Okay, so, and this is updated regularly. I think it's used quite a bit. This is this thing called lmfit. It's nonlinear least squares, minimization, and curve fitting for Python. It's quite extensive. It supports lots of optimization algorithms. It even supports some Bayesian approaches too. The documentation is looks quite long. Okay, yeah, there you go. The latest release was March 2025. Okay, so it's been regularly updated, which is great. So we can exploit these, these updates. There's quite a bit of stuff here. So I'm going to cut through all this and basically show you how you can use this to fit your own model. Okay. All right. So let's start then. Okay. We're going to import a bunch of things to begin with. We're going to import lmfit. Let's see if it's actually available. That's not even available. Okay. So do a pip install. I normally use this for my own desktop environment, so where everything is available, but let's use the Jupyter Notebook. So that's lmfit. That looks like it's ready. Okay. And the other thing I'm going to need is NumPy. That's the big array package. The other thing I'm going to want is to do some plotting. So I'm going to bring in matplotlib. It's a long one to remember. Oh, that is, it remembers me. I think that's all I need for now. So I'll bring those in. So those are in. Okay. So what am I going to fit? I'm going to fit a really simple model. I'm going to show two. I'm going to build this software first with a sort of simple model. Then we're going to make the model a little bit more elaborate and show you what you can do. And then this afternoon, the AI session, I think Joe's roped me in to do some AI stuff as well. So I played around, it's my own fault. I played around the other day with using Claude to write some fitting software for me. I mean, we've done this before, but I hadn't used Claude before. And Claude wrote some really elaborate software, which we can show you this afternoon. And show you what it does. I'm going to show you something really simple here. So, okay, we've got everything imported. I'm going to define the model. Okay, so this is the model we're going to fit. Okay, it'll be a really simple one to begin with. Okay, it's going to be just a single reaction. I know, terribly complicated. Basically mimicking exponential decay. Okay, I'm going to initialize a couple of things. And just to show that make sure it works, I'll do a quick simulation. Just to make sure everything that model is good. Okay, so that's what the model does, and the blue line is the thing I'm going to try and fit. This is because let's pretend experimentally we can only gain access to S1. All right, we can't measure S2, and perhaps I should show you. This is what the kind of thing the lab will actually give us. Oh, oops, what have I done wrong? Oh, comma. Missing comma. Let's pretend this is what the lab has actually given us. Now this is perfect at the moment, but and the lab is not going to collect 100 points. We'll address that shortly when we create some synthetic. We're going to create some synthetic data based on this model. Okay, and we're going to try and fit this model to the synthetic data. We're going to try and estimate K1. Okay, I'm going to assume the experimentalist knows what the initial amount of S1 was, which is 5, but they don't know what K1 is, and the objective is to try to estimate K1. All right. Okay. Okay, so what should we do first? Why don't we create some synthetic data first? So create some synthetic. This is a synthetic experimental data. Okay, so let's create some synthetic experimental data. And to do that, I'm going to reset the model back. Okay, and then I'm going to grab this. That's going to be my data. And the only data I want to collect in this case is S1, right? Because I'm going to add noise to S1, right? That's the experimentally determined one. And this is going to be really, I'm going to do this really easy. I'm just going to, I'm going to, let me see, I'm going to call it experimental data equals M plus, so this is not exactly what I've got in my script, but let's see how it goes. And then here I'm going to have some, I'm going to have a standard deviation, sigma, and I'm going to have so many data points. So let's put number of data points. These are the number, and I haven't defined these yet. So let's define these up here. Num data points. Let's see, the experimentals was able to collect 10 data points. And let's say let's pretend that the amount of noise was 0.1. So we'll be able to change that afterwards. Let me run this and see what it does. Okay, we print the experimental data. Okay. Oops, not quite. X. Oh, let's change that to capital D. That is the experimental. It looks like a lot of it. Oh, it's too much experimental data. Let's go to 10. Oh, is this? This looks like a lot. Why is that? I done wrong there. Oh, let me look at M first. Okay. So what have I done wrong here? Maybe I have to be specific in the columns. Ah, yeah, there you go. So what I've just done there is I had to tell it which column, even though it's only one column, I had to tell it which column in my results I wanted to add this, random noise to the data. So this little bit here is just adding random noise to my perfect data to create experimental data. This is the experimental data here. Actually, that's not the experimental data. That's the experimental data. There you go. That's the experimental data. Okay. All right. So I got some experimental data. So I'm ready now actually to do some fitting. Okay. Now, normally you wouldn't do any of this, of course, because the experimentalist would give you some data. I'm just doing this to create some fake experimental data. Okay.
Herbert, before you go on,
Yeah.
I mean, maybe this is later in your flow. Are you going to look at the experimental data a little, the synthetic data, and
Yeah, why don't we
examine it?
do that? Yeah, why don't we
Okay.
do that? Yeah, so I'm going to do an interesting hack. Yeah, let's do that. In fact, I'm going to I'll need time for this as well. So I'm going to pull out, I'm going to ask it for time as well. I need to change that to 1 so I get this, I get the same experimental data, but I can also now plot it just to show you what the, yeah, we should do that just to see what it looks like. Let's put some, yeah, I think that'll, see, it doesn't look very, actually, God, that's the wrong one, isn't it? Okay. You have to use plot, not auto plot. So I'm going to do, what's 2 variables here, the x-axis and the y-axis. The x-axis is just going to be time, which is that one. And the y-axis is going to be the experimental data. Okay, so now we'll plot that. Doesn't look very noisy. Let's increase the amount of noise to see what happens, shall we? Oh, there you go. See, that's very typical experimental data. Perhaps it's a bit too noisy, but the idea is we can change the amount of noise just by changing sigma. Okay. There's one little issue here, which I'm not going to bother with at the moment, but because I'm just adding normally distributed data, sometimes that can exceed the sometimes that can cause negative concentrations. I'm not going to worry about it at this point because you can see if I increase the noise, we might get that. There, you see this one here. is negative. That's because the normal distribution is centered around 0. And of course, it's producing negative values and positive values. And if the negative value is too big, it could exceed the actual value in the simulation and give you a negative value. I'm not going to worry about that at the moment. It won't affect the fitting, but real experimental data wouldn't have negative concentrations. Okay, so for now we won't worry about that. So there's some experimental data. Okay, so we're ready now to do the fitting, and actually there is that.
Robert, you had a quick question about
Oh, yeah.
explaining the X data generation line.
The X.
Just like, yeah, what line 6 there? What's going on?
6. Oh yeah, line 6. Okay. So so this line 5 to begin with, generates perfect data, and it generates 2 columns for me, time and S1. Okay, and that's perfect data. Now I need to generate imperfect data. I need to keep the same time points, but at the different time points, the S value has to contain some noise in it. Okay, to replicate experimental noise. So I'm doing that with this little thing here. This here, the M here, of course, refers to the M coming back. But now there are 2 columns coming back, time and S1. If I print, this is why I wish I had it. This is where an interactive thing would be handy. Okay. So let me print M. So there's that's what M actually looks like. 2 columns, time and S1. All right. Okay. Now,
a minor thing in case it's a point of confusion, the colon that Herbert used means use all rows. All rows. That's the colon there, and 1 means the first column.
Yeah.
And,
so this,
and Python counts from 0, so that's actually the second column.
Yeah.
Yeah,
So
that's
yeah,
it.
that's right. I'm just going to do that. So, yeah, that notation here looks really weird to most people, and it takes a bit of getting used to. Actually, it took me a while. But as Joe said, the first column, the first thing there, which could be a number, but in this case I put a colon, and the colon means all rows. Okay, and the second one means, well, what columns do you want? I only want 1 column, and that's the column that corresponds to S1. Now, because everything indexes from 0, this is column 0, and this is column 1. So I need to extract column 1. So I'm basically trying to extract all the S1 values. All right. And then what I'm doing is, so this is now a single column that contains all the S1 values. And then I'm going to add to it a whole bunch to each entry in the column. I'm going to add a random number drawn from a normal distribution. This is to try to mimic experimental data. This number here is the mean around which the normal distribution is made. Right, so this means I can get negative as well as positive errors. The sigma is the actual error itself, and that they call it the scale. I think that's the standard deviation.
Yeah, when they use scale, they mean standard deviation.
Yeah, I don't know why they use the word scale. Okay, that's standard deviation, and this is just related to the number of random numbers I want, and I want the same number that's in the. I mean, what I really should do is call that num data points. I basically want the same number that's in the data that's returned. And the number of data points that's returned is 10. And if I'm putting in 10 here, right? So I could increase the number of data points if I want to do, say, 100. And you'll see that's what 100 noisy data points looks like, okay? All right, and I can control the amount of noise just by changing sigma. So let's put that back to 10. Okay, so I got my noisy data. Okay, so the next thing I need to do is, remember what Joe was talking about, these residuals? That's the difference between the fitted model and the data. And I need to compute that. In fact, I need to provide a function to compute that. So lmfit requires a function that will compute the residuals. All right, and I am going to create that function here. So in Python, to create a function, we use the word def. I'm going to call it residual. You can call it whatever you want. I'll call it residuals. And it takes at least 1 argument, which is the, it's actually technically, it's a dictionary, but we won't worry about that for now. it's the list of parameters in your model. Now we've only got one parameter, K1, so there'll only be one in there. That's okay. So this function requires me to compute the residuals. Now, what's peculiar about lmfit, it doesn't require the square of the residuals or the sum of the square of the residuals. It literally wants the difference between the experimental data and the fitted model at each point. So it actually wants you to return an array where each element in the array is the difference between the experimental data point and the current fitted value. And that's what I'm going to do. First of all, I need to grab the current value of the parameter that it's currently being fit. And all I do is do this, hold on, P colon K1, and then value. That will grab the value of K1 from P. That is the current value that it's trying to fit. Okay, I need to grab that. The other thing I need to do, I hope this works here. I need to give that value to RoadRunner so it can recompute the model at this current fitted value. Okay, so I'm going to, and the value of, oh yeah, RoadRunner is R, because I got R up here. Okay, when I loaded the model, there it is. Okay, that's R. And I'm going to assign K1 to the fitted value. The other thing I need to do is, of course, I need to run the simulation from time 0 at the initial starting point. So I'm going to do this very important reset. That is actually crucial. Each time it computes the residuals, you need to reset the model back to the initial conditions, but with the new parameter. Okay. And then finally, I'll just compute I'll run the simulation then. All right, simulate 0 to. Now, I really ought to have, I ought to put, a proper variable here for the time end, which is 50. So that's time end. Okay, that's the time end. And then down here, I'll probably need to rerun this thing now to make sure I get access to time end. That'll be time end. And of course, the number of data points. And what do I need to return? Well, for the residuals, I actually only need S1. Right? That's the only thing I'm collecting is S1. So I'm going to specify, just give me S1, okay? I don't need time. I just want S1. And I now need to then compute the actual residuals itself. And that's going to be the difference between M, what I just simulated, and the experimental data, right? The experimental data stays fixed, right? Because the experimentalist will give you some data. And you've got that fixed, that doesn't change. And so here I need to compute the residuals. And so what I'll do is I will compute experimental data. And this again is going to be one of these so-called slices. It's going to be all rows. It's going to be the first column in the experimental data. I know there's only one column here, but I'm going to specify the 0th column. And I'm going to subtract from it the simulation data. And that again is just all rows. And again, the first column. And I'm going to return this from the function, right? So what's nice about this, these are all vector operations. It's taking the entire column of experimental data and subtracting from it the entire column of simulation data. And it gives me then the difference between the experimental data and the current state of the model. And that's the array of residuals. That's what I'm returning. But this is really the most difficult bit to do, is to compute the residuals. The rest of it, as you'll realize, is not that difficult. All right, so I need to compute the residuals. I've done that. Now I can actually start the fit. The first thing I have to do for LM fit is to tell it, well, what are the parameter names that you're going to fit? Okay, well, I'll create a variable called parameters.
Herbert, you want to unindent.
I think I'll unindent too.
Yeah, okay.
Good one. lmfit parameters. So this will create an lmfit object. For some reason it doesn't like lmfit. Why not? Oh, because I haven't actually imported it. I should import it, shouldn't I? We do that here. We run that again. So I've imported lmfit. I can go all the way down. Now it's happy, you see. Now this call here will create this variable called parameter, which is, I guess I should call it parameters. This is the object that's going to contain all the parameter values, and I'll be able to tell lmfit all about those parameters then. And all I have to do now is basically add the parameters to this object. I'll do add, and it wants the name of the parameter. There's only one. An initial value. Let's say we've no idea what it is. Let's say we'll give it just a value of 1. I mean, I know it's 0.1, okay, up there, but I'll give it a value of 1. And I'm going to tell it the minimum amount. You don't always have to do this, but I'm going to do it here anyway. You have to tell it the bounds in which you think the parameter exists. So I know it can't go below 0 because it's a rate constant. You can't have negative rate constants, right? So I know it can't go below 0. And let's say it can't go above 10. Okay. You'll have to make that judgment yourself, all right? Just the parameters. And actually, that's almost it. All I can do now is, I think there's a shortcut to this, but I'm going to do it this way. I now create the actual fitter object, the thing that's going to do the actual fitting, called lmfit minimizer. There it is. It's actually a capital minimizer. There it is. And I have to give it the name of the function that's going to compute the residuals and my parameters. Okay. Now this thing parameters, well, parameters. Okay. This thing parameters is actually what ends up in the residual call. That's what ends up as P. Okay. So what lmfit will do, it'll call residuals and then pass this parameter thing into the residuals. And that's how I get hold of it. And now we're actually ready to do the fit. So to do the fit, I will go, I'll call the results of my fit result. And then I go fitter, minimize. That's it. Let's run it, see what happens. And what's happened here? Too many indices in an array. Oh, okay, it doesn't like my residuals. What doesn't it like about my residuals? That's odd. What does it not like about my residuals?
Look at the error down below. What does it complain about? What's it
Too
say?
many indices for array. Array is one-dimensional.
Oh, you got a one-dimensional array in there. Which of them is one-dimensional? So experimental data is that? Yeah, I think that's one-dimensional experimental data. The way
you think I can let's try that?
Yeah, you have to redo that. So.
Oh, great, thanks. I think it's done it. Oh, great, that's it. So I told you the residuals function is the trickiest one to write. Okay. All right. What can I do now then? Well, what I can do now is what happened? So let's go result dot. There's a thing called message. Let's run it again. It said fit succeeded. Now that doesn't always mean it succeeded, but it probably does mean it managed to fit the data, the model, sorry. So let's add some more to this. Big one is a report. So I can print result. Let me see, it's lmfit report fit, that's right. And I then hand it the results, and it'll give me lots of information about the fit. There you go. So if you can see that. So this sort of summarizes what happened. It said it took 25 calls for the residual function to make this work. It's confirming I had data points. It's confirming I had one parameter to fit. This is the chi-squared. This is how, how well it fitted. It's also telling me here the actual fit algorithm it used. And this is one of the ones that Joe described. It's basically like a gradient descent. Now, lmfit has a whole load of them. And I'll show you one in a minute. There's a whole load of fitting methods, because this is actually a relatively simple model to fit. I don't think there are any local minima. I think there's probably just one global minimum.
Right, it's a
And-
convex, it's
yeah.
convex surface.
Right, and so it's found this pretty easy to fit. So the gradient-based like algorithm was good enough. The other really important thing, of course, is told us its estimated value for the fitted parameter, and it says K1 is 0.1, 0.103, etc. Then it gives you a plus or minus. So it gives you some estimate of the error, and that error comes from the fact that there's noise in the data. Okay, that's why that is. So that's a pretty good fit, right? Because the actual ground truth is 0.1. Right, so it managed to fit it. So now we can mess around with this and say, well, let's say, you know, the lab was really bad, and it made some really noisy data. Let's see what there's some noisy data. Let's see if things get worse or not. Still managed to fit it. Took a few more iterations to find the fit. The fit hasn't degraded very much, so that's not that bad. So let's do
Oh, wait,
something.
Herbert, before you do the next one, look at the error bars around that estimate.
Yeah, it's gone up a little bit, right? I think.
Right, it's at 27%.
Yeah, so it's gone up a bit. Yeah, so it is less certain as to this
Right.
the value. So let's try, you know, make it really bad. So we got this. Yeah, well, there's pretty much there's pretty no signal there, I don't think. So let's see what it does. Okay. So yeah, this basically failed. Actually, it says it succeeded, but actually the answer is total nonsense because it claims the value of K1 is 8, but look at the error. It's 10 to the
Right.
9. The error is 3 gajillion %. This is complete nonsense. Okay, so don't, when it says fit succeeded, don't always believe it. Okay, it has some other criterion for deciding whether it's fitted or not. Obviously, looking at these two values is not, or at least the error is not one of those. So anyway, so there's a
I mean,
nice
0.1 is in that range, so.
I get it depends on your criteria.
The point one is it in the range? Yeah, right.
Right.
I mean, I can reduce the amount of error. Well, that's awful. Yeah. Only 200% error now. Nice, and it's got to 0.33. All right, so that's the general approach how you can sort of manually put together this fitting method. It's not that difficult. As I said, the trickiest bit is putting together the residuals. You have to be aware, and I made that mistake. You have to be aware of the dimensions of these two arrays so you can subtract them properly. And the one that is easy to forget is this reset. Even the AIs forget that one, by the way. But humans also will forget that. You must reset the simulator back to the beginning every time it wants to compute the residuals. All right. So let's try a
But before we go on, I just wanted to sort of underscore line 9 in your script there.
Oh yeah.
So that choice of your min and your max is really crucial. Herbert, if you change the max to 0.001, so the true value is 0.1, and then if you run this, you know, it will come up with an estimate within that range.
Yeah,
right?
It's hitting the upper limit.
Yeah, it's hitting the upper limit, and so this is something you have when it hits the upper limit, your max. You know you don't have your max large enough, and so you might ask the question: why don't I set the max to 10 to the 9th? And the reason is you've given it a heck of a lot of work to do. So you may want to pick lower numbers and inch your way up, and then as you inch your way up, you reset the min as well as the max, so it's working with fewer of smaller range. It requires less work.
Mm-hmm. Yeah. Okay. What I'm going to do now is I'm going to grab this wholesale, this model. Okay. This is by the way the spider ID. This is the one I tend to use. But I'm going to just grab this and I'm going to paste it in. Where did it go? Ooh, where are you? Here. I'm going to paste this in. I'm going to start a new one. Okay. Start a new notebook. Start from scratch. I will have to. I think I will have to install Tellurium and LMFit. All right, so won't take a minute or two. Then what I'm going to do, I'm just going to paste that whole code in, and I'll show you. It's basically the same code, but it does some plotting as well. I added some plotting, and the model is much more elaborate. And you'll see what we have. And this afternoon, got an even more elaborate one to show you as well. Okay, so I think that's it. Now to reset the runtime. Hopefully, I'll check first that. Oops. I told you, typing Tellurium all the time is error prone. And see, I told you it was error prone. So that's why we shorten it to TE, okay, because it's such a nuisance to type. Okay, so I'm going to paste. So I've just pasted in the entire code. Let me briefly go over this. So I'm importing a bunch of stuff here. Actually, I don't need to import RoadRunner. So this model is the one we saw yesterday. It's actually the Heinrich oscillating model. So we're going to try and fit, there's 4 parameters I'm going to fit, V0, K2, V0, K3, K4, and K5. So 4 parameters we're going to try and fit to this model. And this is an oscillatory model. This is the residual function. It's very similar to the last one I did. I do a reset at the beginning. I pull out all the values that have been given to me during the fit, and I'm assigning them to RoadRunner. All right, so RoadRunner has the new values. I'm doing the simulation, and I'm collecting 2. I'm assuming now the experimentalist can collect data on S1 and S2. Okay. And then this bit here is just computing the residuals. I'm doing this in a long-winded way just to show you what's happening. But for each column in model, I'm computing the residuals. That's each column, okay? And then I'm using this special NumPy called HStack. What that stands for is horizontal stack. It's basically stacking A1 on top of A2, forming A3, and then it's returning the entire thing. So the residuals function, it doesn't care about the order of anything, but it just wants one long array containing the residuals. All right, so I could swap A1 and A2, it doesn't matter. I could put, A2 here and A1 there, it doesn't matter. But it does want one column of residuals, and that one column could be very long, okay? If you have a lot of data, your residuals, there'll be a lot of residuals on this column would be quite long. So then I just return it. This bit here is just the synthetic data creation that we saw before. I'm creating synthetic data for S1 and S2. There's my sigma for the error. And then here, I'm building my LM fit structure. So that's the parameters. There's 4 of them, okay? Here I'm doing something slightly different because I can run this multiple times if I want. So I'm actually adding random values to the initial values for the constants. All right, just because I can. Then I'm creating the fitter. We did that before. And here I have 2 actual minimizing calls. One of them I've commented out, the other one I've not. The difference is that this one, I'm specifying a different optimizer. And this optimizer is a non-gradient descent optimizer. It uses a sort of evolutionary approach. So it's very good at finding global minima if there are lots of local minima. Okay, and this model has that potential because it's quite, it's nonlinear, it's oscillating. There's a potential here for local minima, so I'm putting this in as an option. Okay, I do the fit, I report the results, and then the rest of this is just plotting. I'm just plotting the original experimental data. That's what I'm doing here, plotting the original experimental data, and then I'm also plotting the fitted one. Okay, all right. So let's run this, see what happens. Okay, that's pretty quick, right? This time, notice it's done 800 function evaluations, right? 800. Now, to be honest with you, these are actually quite modest numbers. In my textbook, I go through all this in my textbook. Some of the models there took millions of function evaluations, right? Millions. So this is quite modest. That's interesting. Yeah. So it's saying here it wasn't able to estimate the uncertainties. The reason for that is because it actually, I think it's because it found it difficult to do the fit. And it can't guarantee that its estimates are going to be accurate. So it just didn't tell you. We can try it again.
Like
and
the
it
method
may...
itself doesn't do uncertainties. It says.
Oh, hold on. I'm going. Oh, I'm running the wrong one. I'm doing Nelder and Mead. Hold on. Why? Oh, you know what? Look at this. Can anybody guess the problem? It's a typo. That should be least.
Oh, last square instead of least
Should
square.
be least square.
So it just merrily went on and didn't complain.
It picked. So those of you, I don't know if any of you have heard of Nelder and Mead. This was when I was so-called growing up. This is a popular one because it's actually, it mimics a sort of spider that's crawling, you know, along the search surface looking for the global minimum. I don't think it's that great by today's standards, but it was good then. But it still works. But it's not a gradient descent method. And if you don't use a gradient descent method, you cannot get estimates for the errors in the way that this program works. So Nelder Mead is not gradient descent, so it doesn't give me any uncertainties. But actually, it did a decent fit though. Let me just run this again. Okay, now we have the least square. This is this gradient descent method. Now it gives me some estimates for the errors. And this is the actual fit. So the dots, the little dots are my experimental data, and you can see it's oscillating, right? This is an oscillating model. These are not regular oscillations either. You can see it's really, they don't look quite symmetrical. And the red line and the green line, that's the fit. And you can see it's actually a pretty good fit. All right. And the errors are very modest, you know, less than 1% or so. And I know these fits are pretty close as well to the ground truth. Now, what I can do is of course, we're going to be mean to the program and make things worse. And we'll see what happens. Okay, so this completely failed, right? So, I mean, I think that I can see a pattern. As a human, I can actually see a vague pattern in the data points. But the fail is actually, the fit has actually failed. We can tell that. What happens though, if I switch to...
Did it think that it had failed?
No, it didn't.
Okay, yeah.
It's very optimistic. Let me fit to a different optimizer. Now this one will take longer. You can see there's a bit of delay here. And look, it had actually a decent attempt at doing the fit. And it's actually the actual, you know, the green and the red are actually the fitted model, and it's actually managed to do the fit. And you'll find that difference often between the gradient descent methods and these other, you know, non-gradient descent methods. I mean, I can run this again. I mean, it won't always get it, but yeah, that's not quite right because you know that the frequency is much less. I mean, the error is quite significant in this data. That again, it didn't really work. Now the gradient descent is likely to fail every time. Actually, if I were to give it a bit better data, it'll do a much better job. Notice it takes a little bit longer. No, that's not bad at all. That's pretty good. And yeah, you see the data is pretty noisy, but it actually did a fairly decent fit, surprisingly, actually. So if I did this with I comment out the evolution one and use the gradient descent fitter, it actually did it as well. It's fairly stochastic because the initial conditions are always different and the search is always slightly different. Sometimes it'll make it, sometimes it won't. Try again.
Which points out, you know, in terms of your workflow for parameter fitting, you may very well want to try several times.
Yeah, you do want to try several times.
Right. And the other thing, Herbert, just as a
Yeah.
sidebar, I think folks want to make sure that you save this notebook.
Oh yeah, of course, yeah. If we have yeah, there's a folder called AI generated. I can put this into the into that folder if you like, and I'll call it not human generated. Okay. So yeah. So it's interesting. You'll probably see this afternoon, but one of the uses of AI is to actually generate this code for you, and it does actually a reasonable job. And we've got two examples, one from ChatGPT. Joe may have one from Gemini, I'm not sure. I have also another one come from Claude, and they're all quite different. And the Claude one is very elaborate. It did make a mistake, and it took a few rounds of talking with it to figure out the mistake. But once we realized the mistake, it was very excited to be able to run this properly. And as I said, what it outputs though is very elaborate, and I won't show that until this afternoon. But it's pretty impressive. But in order to use AI though, I had to know a little bit about what was going on. Because in the end, I was the one that spotted the error. Now we worked together on it. I said, well, produce a stripped down version. Maybe we can isolate the problem that way. And it said, yeah, that's a great idea. So I produced a stripped down version, and then I spotted the problem. It never spotted the problem. So I think with AI, you have to think of it as a partnership. It's not a thing telling you an answer and that's just the end of it. It's actually a back and forth between it and you, because it doesn't always get it right. But but when you work like that, it can be a super time saver. Okay.
Someone has a question about
yeah.
what methods are available and which ones you like. There's
Oh yeah,
someone
good
found a
idea.
link of like literally everything, but
I know. Yeah, good. Yeah,
there's a
good point.
bajillion of them, yeah.
Let me see.
There's a link in the chat that actually links
Yeah.
to the.
I think
okay.
we've taught a class on computational
Yeah.
biology
Oh,
for
yeah.
several years. And I think, at least for me personally, the conclusion I've come to is I think that Nelder-Me or least squares, something that's going to do great, just straight gradient descent, is a great one to try because it's fast. Maybe you try it with multiple starting points. And then if that's the other thing you should try is the differential evolution, which is a global technique, which we'll try a lot of them. And I haven't, beyond that, I mean, occasionally something else might work better, but it's not really worth the effort.
No, I agree with Joe. You might as well try least squares to begin with, just in case, because it's quick. And you get some rough error estimates automatically from that. But if that doesn't work, then I would just switch to differential evolution. If that doesn't work, which is pretty rare, you can try some of the others, but it probably means there's some real problems with your data.
And the other thing is also your workflow. So this whole discussion about starting points, when you describe your parameters in the LMFit parameter statement, you specify the initial value, a min, and a max. That's another thing to play around with.
Yeah.
Is, maybe the range is wrong. It's not big enough, or it's too big. Maybe the initial values, maybe need to try a few different initial values. I find that that's another one that's very, very powerful tuning knob that sometimes people overlook.
I can show you one other thing, which I meant to do is you can actually combine these algorithms. So you can start with differential evolution, and then you can just switch over to least squares. Now I can't remember at this point actually whether I have to, and I'm going to do it just in case, and to make sure I update.
I think you have to update the starting value of the parameters. I think that's the one. So yeah, you're going to do what, differential evolution and then LMFit.
Yeah, let me see, where is it? I got a feeling you have to do this, and then here then becomes whatever the current fit values are. Okay,
right, exactly.
I got a feeling you have to do that. Otherwise, you
And just while Herbert's working on this, I think part of the logic that Herbert had for doing it in this order, first differential evolution, then LM fit, is differential evolution is not guaranteed to find a local minima. And so if you're, on the side of a hill, then the least squares will then get you to at least what the local minima is.
Yeah, so just to reiterate what I've done here is I'm starting with the differential evolution, because I'm assuming this is a hard problem, right, to solve. So I'll start with that one. Then I'm reinitializing the parameter values with the new values that came out of the differential evolution. And I know they're in RoadRunner, okay? So I'm going to pull them out of RoadRunner and create a new parameters object. And then I'm going to feed this into the least squares. No, I need to, hold on, I need to, no, I need to create a new minimizer as well. Oops, make sure I do that. Down here, I'm going to create a new minimizer as well, because I need to pass in the new parameters, okay?
Right.
So now they follow on from each other. And so you get the best of both worlds now. So you'll get, you'll be able to tackle hard problems, but with the least squares, it'll start off from that point and also give you some estimates for the errors. So if you run this, so you notice the differential evolution does take a little longer. And now I get all this, and it gives me the error estimates as well. Now, I should warn you, these error estimates are very approximate. And actually, in a research paper, I would not use these. These are just good here for this, for running this kind of thing, just to give you an idea. For a research paper, you need to use, I think Joe mentioned it, either bootstrapping or profile likelihood, which basically, the bootstrap basically, it creates synthetic data set, new synthetic data sets from your existing experimental data set using the errors that it finds in your experimental data. And then it runs those on the optimizer. It may do this like, 10,000 times. And from that, it gets a truer estimate of the uncertainty in your parameters. So we don't have time to go over that, but if you buy my textbook, it's in the textbook. These are great just to have a quick look to see what's going on. But if you try to publish this, a reviewer is likely to push back on you and say you need to do better estimates. And the Bayesian approaches do this automatically. There's probably one reason why people like them, because it's sort of built into the Bayesian approach that it tries to give you accurate estimates of the uncertainties. But they are very slow to run, and they have convergence issues, which you have to be very careful of. So we use Bayesian stuff, Bayesian estimation in another project, and they can take days to run, and you have to run them multiple times to make sure that the Monte Carlo estimation is converged. You could end up in real trouble. So, but to begin with, you can do this kind of thing and see what they look like. So the other thing we'll do this afternoon is one of the things that you need to be aware of. Experimentalists won't be able to produce all the data you want. So in this case, they may only be able to produce S1, for example, or only S2. And the question is then, what happens if we only have limited data? And so one of the things that we might be able to explore this afternoon is what happens when you have limited data. So my feeling on parameter estimation is that you should do an in silico study first. So you're working with an experimentalist, and you want to tell the experimentalist, well, can you collect this? Can you collect that? What you could do is an in silico experiment to explore, given the model, what kinds of data would maximize the likelihood you'll get a good fit. And then you can go back to the experimentalist and say, well, if you could collect this and this would be really great. The next best thing is if maybe you can't collect this one or the other. I'll show you what I mean by this afternoon. Okay. So
That's an interesting thought. I don't think we usually discuss in our
No,
class, but I mean,
no.
some conversation up front about what's easy and what's hard to get
Yeah.
would
And then
be
you can-
great. Yeah.
Yeah, and then you can do an in silico study yourself to see, well, is that good enough?
Right. Exactly.
And do I need to go back to the experimentalists to say, well, we really, really need these other kinds of data, otherwise it won't work.
Yeah. That's a really
Yeah.
good idea.
And given that experiments today cost so much to do, and computation is relatively cheap, it's probably a wise thing to do anyway. So, okay.
There's a little bit of discussion online about the
Yeah.
just other searches, like there's second order gradient methods, like the BFGS method and the Newton.
They're all problematic. Of the gradient descent methods, what least squares, it doesn't tell you here, but this, oh, it does. It uses the Liebenberg markup. That is probably by far the best gradient descent method there is. It's pretty good. It's a combination of methods. And it starts off with a raw gradient descent, and it just goes downhill. But when it gets closer, it switches to a new method where it assumes a certain structure for the minimum, and that allows it to get to the minimum very, very fast. I mean, if the Liebenberg markup doesn't work, you can try the others, but the Liebenberg markup is usually pretty good. So,
Another consideration is how much noise you have in the data. The problem with taking higher order derivatives or higher order differences is very sensitive to noise.
yeah, derivatives are always notoriously bad to estimate when you have noise. So integration, if you can do integration, do that. Because that averages out
That's
the
a
noise.
smoother. Yep.
Smoother, yeah. Okay, what else we got here? True size grows too fast. Oh yeah. Yeah, the Hessian is the second order. Somebody says in the chat, the Hessian is the second order estimate. I mean, there are tricks to estimate that. I mean, it's generally slow to estimate. The second order and it's noisy as a result. There are tricks to get around that by using first order estimates, but it's problematic. So, yeah. Yeah, so as an experimentalist, I appreciate the upfront conversation. Yeah, it's really important to talk to the experimentalists as soon as you can, because they will tell you what they can and cannot do. And then you can figure out whether that's enough or whether you have to go back to them and say, we really need, a bit more. So that's important. This is why when an experimentalist comes to you and says, I have data, let's build model, that is always a bad idea. So they'll just,
And already too late at that
it's
point.
really a bit too late, yeah. So work with them from day one, then you'll be good. Okay, well, I think it's probably lunchtime, well, for us in the West Coast. Let me see. I'll copy these files to the drive. So what we've got left is it's just the modeling stuff. So we can have if there's anything you want to discuss, we can discuss that. Otherwise we'll break for lunch and come back.
Oh, we're back at what, West Coast time, 1:30, an hour and a half roughly, or what do you
Yeah.
want to do? Okay.
Yeah, let's see. It's 1:15. Well, since it's all 1:15, we could come back at we can come back at 1:30, 1:30 West Coast time.
So that's 1 hour and 15 minutes from now.
Yeah,
Exactly.
I think that's a good time. Yeah.
Sounds great.
All right, everybody. We'll see you in an hour and 15 minutes.
Britt, did you save that file to that directory?
Yeah, where did I save it to? Good point.
Yeah, who knows, right?
Yeah, that's always a challenge with what I usually have to do is I have to download it onto my machine and then I can upload it. I've not really found a way to move things around on.
In theory, you can like right click and do the move.
I know
theory,
that,
right.
Finding
But
it,
in practice,
I'll just pull them straight from my drive. I got them because I developed them all under Spider, you see.
Okay,
So
cool.
I will.
Well, and the one you were just working on also, make sure that's in that file somewhere.
That
Did that end
should
up there?
be
Right.
that's the one I was working on. Yeah.
Okay. And we'll do the same for the AI sessions, which will have a lot of
Yeah.
collab in it.
Yeah.
So we'll make sure we save those.
Where did it go to? Oh, here we go.
Yeah, it looks like it's not in there.
So I got I'll just change that to human. Differentiate us from our overlords. So where is it? There's one. That's the exponential fit one. The oscillating one is human.
So I was going to drop off unless you need to coordinate with me for this.
No, we were good. I think so.
Okay,
We're okay.
great.
Okay, great.
See it when.
All right.
Yeah.
Started, Hunter. All right. Okay, so in this section here, this is an experimental section of the summer school, and it's something that Herbert and I in particular have been reflecting on in terms of our teaching, and that is how has AI influenced what we do with our computational biology class and then other related computational courses. And so what we've done is as a starting point, we went through primarily the homework for it's a 1/4 class at the University of Washington, and just tried the experiment of, okay, so let's throw these problems to ChatGPT or Gemini or Claude that we would use for the homework and see how well it does, just to see if, do our students really have to attend class to do the homework? And surprisingly, I did this with Gemini. It got everything right. Just, type in the question, it gives you the answer, and it looks good. So it took us, surprised that it was that good. It worked that well, and sort of caused us to take a step backwards and ask a lot of questions about what it is we should be teaching. Because I mean, certainly the students have to know the fundamentals. Like Herbert just recently went through the stuff with parameter fitting. But that's the reality is that's not in practice how they're going to do it. They're not going to do all this manual stuff. They're going to take advantage of great tools. So we have to be able to teach about the tools and teach in a way so that we're testing on the assumption that they're using the tools. So that's sort of the genesis of this section. And what I'm going to do in this part is sort of give you provide a little bit of background so that you understand, sort of the general area, the AI area. Now, what I'm going to do, I assume this is a technical audience. I assume you've all seen neural networks. Many of you have programmed neural networks. I mean, I'll briefly show a little bit about neural networks and deep neural networks, but that's not my focus here. There's so many materials available, and many of you have already seen this, so I don't want to bore you by going through all that again. Instead, I'm going to do something a little bit different and give you sort of a perspective about where things are going. Now, this is going to be a sort of my personal journey. I am not an AI research expert. That said, you typically think of AI in sort of 3 stages. There's an early stage with primarily search stuff and expert systems, and now the more machine learning based approach. So I did have a brief sort of cameo contribution to something with the expert system phase. So I feel like I'm sort of AI adjacent and give you my own perspective about where things are going and where they've come from. So maybe have a better sense of how it all fits together. Hopefully you at least find it entertaining. So, okay, I included a little bit on Colab just to make sure you had Colab, but you've got Colab. So, okay, so this is the big question. What is artificial intelligence? So I mentioned before, I'm trained as a computer scientist, and I think one thing that the field of computer science is really good at is buzzwords. So artificial intelligence is a great one, well, definitely it's artificial. There's no question about that. But is it intelligence? That's the other question. So naturally, if I want to get an answer to this question, I asked an AI, what is artificial intelligence? It actually gave a pretty decent answer. we'll get back to this in a second about, how you come up with these decent answers, but it's, these are tools that will, include a certain sort of reasoning as well. And I'll get back to some discussion about that in a second. Generally speaking, AI refers to tasks, not technologies. So years ago, in that sort of the first phase of AI, and actually, let me go through the different phases. So in like the 50s, 60s, there was a phase of artificial intelligence, which was really about search, especially backtrack searching. Very important algorithmic developments resulted from that first phase. But it was quickly discovered that, for a problem like chess, you couldn't search the entire space. This goes back to the discussion I had about computational complexity of doing parameter fitting. I mean, it's just too large. You can't cover every possibility. That's not the way to do it. And what followed that, and actually, another example for the next phase, is what's commonly referred to as an AI winter. I don't know, you probably heard of this, like an atomic winter. So it's sort of like people got very discouraged with the field, said, yeah, great buzzword, but really you can't do it. So that was sort of the first phase, went into the 60s. And sometime late 60s or so, researchers at Carnegie Mellon University primarily came up with this idea about, the problem we have with search is we're not giving it any human guidance. We need to give it some insights as to how to do the search. And that came up with this notion of what's called an expert system. This would be a system that incorporates some human intelligence. So the human intelligence was incorporated in terms of rules, really if-then rules, and that these would be acquired by a this is another great buzzword, knowledge engineer. This is with someone who has computer science training, knows something about the domain, and would talk to an expert like a doctor or a computer person who's really an expert at configuring computers, and would incorporate a body of knowledge in terms of if-then rules. And so I think one of the main things that came out of this was a new technology, really sort of just a fancy data structure called a reading network that allowed you to do very scalable matching of the rules with which ones are available or satisfied. Their ifs are satisfied, so you can efficiently then execute the then part. And I had some modest connection with this when I was at IBM Research, where we developed a new language that integrated a standard procedural language. At that time, it was another very dated thing. PL1, programming language 1. Think of it, like C or Java or any of these other languages. This is pre-object oriented, and it integrated this notion of this fast matching with the reading network with the procedural part as well. So what I think the outcome of this phase was that you found that you could do really great demos, cool demos, like if someone, put in like 2 or 3 rules and wow, it can make this inference. It had this very nice characteristic that since it made an inference from if-then rules provided by human beings, it could also repeat the rules that it gave and provide a kind of explanation, which is, something we don't get today from the, machine learning approaches, which are really just data driven. So that part was all appealing. But what we found was we use the term computational crack. So you go to a drug dealer and the first vial is free, and after that it started costing you more and more. The same thing with the rules. 4 or 5 rules, fine, but what about 100 or 1,000 rules? What do you do with all that? How do you know which ones are consistent with the other rules? So it sort of broke on its own weight. And, as with the first phase in AI, the second phase also followed with an AI winter, where, nobody wanted to touch it. This is bad news. This is not going to work. So that persisted. Now, in the background, there were folks who were got some great funding from secure sources, what used to be secure, at least like the National Science Foundation, and working on sort of fundamental principles in computing more, and looking at neural networks and other related concepts when we're data driven. A fellow by the name of Fred Jelinek, who was also at IBM Research, was working on the problem of voice dictation. There was that was state of the art at the time. This was like early 90s or so, and he made some great progress. And the challenge there was, could you make it so it was speaker independent? We could train for an individual speaker, but could we make it so they could understand any speaker? And speaker independent was sort of like always over the horizon. Never quite got there. And there were companies like Dragon Systems that tried to develop these technologies. That sort of puttered on until we got to the point where we had enough compute. And of course, this was sort of like very early days of the internet. It wasn't called the internet, it was the ARPANET. And once we got enough data out there, so that now we could start training massively with big compute. And so companies, like Google could do this kind of thing, and Microsoft, obviously Facebook could do these kinds of things. So we're talking about 2000s now, when this kind of thing is starting to go on. But one of the things which is a real impediment to be successful here is that to train, you think back to our parameter estimation problem, we gave it some data. We had to collect that data. That's a real hard part of the problem. And that's essentially the label that says this is right. Or if I want to train on sentiment analysis, you got to give me data that shows me for this text, this is a positive sentiment or this is a negative sentiment. So who labels all these data? Now we're back to this, really tough problem about how do we scale up enough data that's labeled so we can train our systems given all this massive compute. Got a lot of data out there, but it's not labeled. It's unlabeled data. And the answer to that was a really cool innovation, which is where, is part of the origin of the large language models. The term language model has a particular technical definition. What it is a language model is a learner that given a sequence of words, like a part of a sentence, it can accurately predict the next word. And that is wonderful because in terms of training, I can use any text now. I don't have to have a human being go in and label this as good sentiment or bad sentiment. All I've got to the way my label is, what is the next word? Whatever that next word is, that's my training. And so now I can train at massive scale. And it's really all about how much text can I pull in, which right now, state of the art, is the entire internet, and how much compute do I have available? And basically, I need more compute if I'm going to have more parameters to estimate. Again, just like what we did with parameter estimation. And that's really sort of the state of the art today, is where we are, is based on, there's a whole bunch of variations on that I will give you shortly. This is an area with a lot of depth to it. I do not claim to be strongly knowledgeable about the full depth, but I can give you, this was really sort of a sense of my personal perspective about the journey that's happened over the last few decades. Okay. And the set of tasks do change over time. So, I mean, it used to be that chess was a hard problem, and now you can get it on your phone, probably on your wristwatch if you wanted. Okay, so just a few things, and this is really more reminders rather than anything else. I assume that almost all of you have seen this kind of thing before. So there's a concept of a neuron or perceptron, and this is really the basic computing element. And what it's done is it's set up very nicely to work fast with specialized kind of processors, although that wasn't the original idea, but that's the way it's worked. And the idea is this, is that you have numeric inputs, and they could actually be vectors as well. Then this way, I just call them x1, x2, x3. Typically, it's much, it's much more than 3. It's thousands of these that are coming in. And what you do is you add these. You're going to essentially do a summation of these weights with the x's, and then you do a step prediction. This is what's called a ReLU unit that combines them. So it's linear as long as everything is non-zero. And if it's less than 0, it goes to 0. There are the earlier versions of this are what are called sigmoidal functions, and they were more complicated. But I think over time, people have found that ReLU works very well for many problems, and it can be done very fast with vector processors. So like GPUs you see talked about a lot, and that's because these calculations can be done blindingly fast. So this is your basic element that you've got. And then we go from there. So the next step is what's called a feed-forward neural network. Again, I assume folks have probably seen this like lots of times. You have all these inputs over here. Each one of the circles is a neuron. The hidden units are what isn't input or output. Essentially, these things here in the middle are where significant calculations are done, and there are different ways of combining things to produce the output. That's sort of like the next step in terms of concept of what goes on with the these neural network models. And the one where we are today, this notion of deep learning, involves a lot of complicated, what the term is, architectures that combine variations on feed-forward networks, variations on aggregating the inputs into various ways. So you'll see the term softmax. So if you want something that's a classifier, you essentially construct a probability distribution of whatever the values of these outputs are. This notion of attention. I call this out in particular because that has really been transformative in terms of the success of many of these systems for language. The challenge always was that as you go from step to step, like if these are numerical encodings of natural language, and you go to the next step, you've got some sort of processing on what was at the last step and so on. By just doing it this sort of stepwise way, you lose information about long-term relationships. You can imagine you say a sentence like, my mother went to the store, and then the next sentence is, she bought a pair of shoes. What does she refer to? She is in the previous sentence. I may have lost that because of this transformation. And that's what attention is all about, is maintaining that connection between other things. It's been a big transformation. It's actually sort of non-trivial to understand exactly what it's doing, but it's a very powerful kind of concept. Anyway, these innovations over the last several years, which are now going at a blinding pace in universities all around the planet, have really driven forward the capabilities of these architectures, at least in terms of scale. And so up until, I forgot to do this chart, but I think up until recently, I don't know if it still persists, you would see this curve where there are a lot of benchmarks that have been developed for the quality of these deep learning models. And you would see that as you increase the amount of text and as you increase the number of parameters, because these W's over here are the parameters. These are parameters that ultimately have to be estimated, that you get better and better performance. And I think we may be starting to plateau on that, but at least until recently. And this is where you read all the newspaper reports about gee, how many how much electricity AI is going to suck from the grid. How much does it cost to run something? It's all about estimating these parameters over here because we're getting more and more of them. I think that's, okay. So, so a large language model is one of these deep learning models over here that inputs a sequence of words, your question, and it outputs an answer. That's exactly what it does. And the way it does this is because it has been trained on one of these unsupervised data sets, which is really basically all the text in the internet. And now they're actually, the current state of things is going from text to other modal data. So it could be pictures, it could be movies. That's where the sort of the next push is right now, as far as I can tell. And so what they do is they create these large language models, which are sort of the base models, and there are lots of them available for free. And then there's what's called fine tuning, where you take that and try to apply it to a specific task. So, okay, and the trained neural network, we have to train all these weights. And we're really talking about any serious model today is in, the tens or hundreds of billions. The top ones, I think, are probably approaching, if not surpassed, trillions. I don't know exactly, others may know, but a large number of these weights. So one of the things, if you take a step backwards here, even though we're training this on all of the data on the internet, some researchers have done the analysis to see, well, really, are we potentially overtraining? In other words, do we have enough data to actually estimate, 100 billion parameters? It's the same challenge we have with parameter estimation for our biological models. And the answer is no, we actually don't have enough data. These networks are highly over-parameterized. That means we have many more parameters than we have data available to train them. And so one of the questions is, Now, what are these extra parameters actually doing? And there was a paper that Herbert shared with folks in his lab about this one hypothesis. It's called the lottery ticket hypothesis. And one of the observations, there are a couple of premise observations that go into this analysis. So the first one is, and this has been known for some time, if you take one of these neural networks with, let's say, 100 billion parameters, and you train it to do something, this just as a large language model, let's say you train it. And then you go and start looking at the weights, and you start seeing that, hey, wait a second. A lot of these weights are pretty close to zero. Matter of fact, probably 95% of the weights are close to zero. And I told you how this function works. It's linear, except for if it's less than zero, then it's zero. So if this is close to zero, that input doesn't matter. This weight doesn't matter. So if you do what's called pruning, get rid of all the weights, probably like 90% of the weights you can get rid of, and then evaluate its performance on tasks, does just as well as the other network with all the weights. So there's a bit of theory behind this, which is sort of interesting. There's something called the universal approximation theorem. It was developed in the 80s. It was done for a slightly different combining function over here called a sigmoid function, but there's an extension of it that applies to this particular Rayleigh function too. And that is that you actually only need 3 layers in your neural network. If you're allowing an unlimited number of neurons in that middle layer, you only need 3 layers. You don't need a deep network. You don't need any of this fancy stuff to actually run it. But what you do need is something fancy to learn what that one hidden layer network is. So that's sort of the first observation. The second observation is that what's involved with learning. And you're going through this iterative, what's called the training, where you're giving it the true values. And in our case, like with a language model, it's like what the next word is, presenting all these problems to it. And so this lottery hypothesis said what's going on is by having these complicated networks over here, we're able to explore different combinations of neurons that work together to solve the problem. And essentially what we've done is we highly parallelize the learning process. And by parallelizing the learning process, we more quickly get to the point where we figure out what's the one hidden layer of neurons. So anyway, it gives you sort of a feeling for some of the thoughts that are going on that are more, on the frontier of where things are. Okay, so large language models. We will be mostly doing stuff with large language models. That's these things that learn off of text and predict the next word. That's their foundational training. So Claude, ChatGPT, Gemini, these are all large language models. So the way they work, I've sort of hinted to this already. There's what's called pre-training. That builds the foundational language understanding. That's the predict the next word type of training. And then over here, you do what's called fine tuning. That's a second level of training that works off of that first one with a smaller data set, less computationally intensive. And once everything is trained, then you have the interactions that you see as a user of the large language model. You ask it a question, it gives you an answer, and pretty impressive kinds of performance in most cases. So what I wanted to do here, this slide is I'm not giving you fact, I'm giving you my judgment as, not a professional AI researcher, but someone who's been sort of adjacent to the AI area about what's going on here. And actually, Herbert and I have had some great conversations about this, very stimulating, about, are these things really intelligent? Well, they sort of act intelligent, but are they? Do they really understand? Don't they understand what's going on? So here's my take on this. There's a term you can actually, I'm not the one who invented this, others have used it, that we have search engines. That was the technology that Google pioneered, where you would find, you type in some text, just plain text. You didn't have to know SQL or anything, and it would come back with a bunch of pages. And then usually with the first
within the first 5 pages or so, you would find what you wanted, but it was sort of low level stuff. Like if I wanted to find out how to change the font sizes on my x-axis in Matplotlib, if that was the query I wanted, it may not give me that. I mean, maybe point me to a Stack Overflow page that might have some parts of that, but I'd have a little bit of code snippet. I'd have to go to something else to figure out something else. And then just getting the right keywords was a problem too with the search engines, because I would usually find I have to interact. I had to replace a part of my gutter, the thing that protects it from leaves. I didn't know the technical term for that. So I started out with downspout protector and eventually got to, it's called a gutter guard, in case anybody out there is trying to, replace their, protect their leaves. It's called a gutter guard. Anyway, that's one of the challenges with the search engines is you got to figure out the right terms to use. So the advance with the answer engine is because it has some kind of, and this is in heavy air quotes, it has this answer engine capability. It sort of understands language to some degree. I don't have to use the right words. I can use something that I could use the word like downspout protector. It actually comes back with information about gutter guards, and it gives me the answer right away. So it's done a certain amount of transitivity because it can make these connections. It knows, words that are, sort of like other words. What are reasonable synonyms? I don't have to have the exact name right. And so that to me is the core value proposition of today's LLMs. Now, things are changing really rapidly. In 2 years, 5 years, it may be very different. And then we may all agree, yeah, this is intelligent. But today, I don't think we're quite there yet. But what we do have is something that can do this sort of transitivity or inference to figure out from language, what did I mean by what I said? Okay, so I think that's my opinion about what's going on there. So you get this associated search by understanding language, common. Now this is important. Good responses to common, that should probably be in bold, questions. Why do I say common questions? I say common because the way it works today is you have to have a few examples of what you're looking for. If it's the term in AI is called a frontier problem, that's a problem that nobody really knows the answer to, or it's really poorly studied. Well, if nobody knows the answer, there's no text out there that, the LLM can learn from. The language model isn't going to be there, isn't going to have trained on that. So chances are you're probably not going to find it. Now, sometimes we get surprised, but I think a lot of times those surprises are somewhere, somehow got buried the answer, and we as human beings didn't pick it up. So that's a value. But I think that's also part of this associative search capability of an answer engine. Anyway, that's my take on it. It's certainly going to give you good responses to common questions. There's a whole art associated with, you've probably heard the term prompt engineering. How do you ask the question? Makes a difference. The guidance typically is be specific, give some examples, and ideally even identify the steps required to solve the problem if you have a problem. And one of the key issues today, which I think there are technical solutions to this, but this is something, if you're using it today, current state of the art, are what are called hallucinations. It doesn't know, but boy, is it happy to answer. I know a lot of people the ages of my children who are very much like that. Boy, will they give me an answer. They don't know. So anyway, I think that's sort of my take on this. I think I'm just about at time for this part. Let me open it up and see. I haven't checked to see. I don't know if there are questions at this point. Before I go into the next step is I'm going to go into details about actually using one particular LLM for computational biology. But before I go on, this is sort of the philosophy. Any thoughts, questions, comments? Okay, well, either I'm perfectly clear or it's very late in Europe, and so it's another possibility. Okay, all right, so I will go on to the next part. This part I'm going to share with Herbert, but I'm going to start. I'll get you started, and we'll do it from there. Okay, so this here is, let's see, is this the one? Yeah, let me put this in the chat. So you have access to it. So this is a notebook that I will save. It is being saved, and you'll have access to it. That's sort of the bare bones. The original notebook is going to be also in the same, hopefully also available to you too. Let's see, where am I? Oh, here's my chat. Here it is. Okay, so there's the notebook. All right, I probably have to rerun this again. Restart session. Probably is timed out. Okay, so what I'm going to do with this is, so let's talk about context here. So this is Google Colab, and you've had exposure to this. Herbert did quite a bit with this today. So it provides a Python programming environment. Let's see if that succeeded or if I have to do something here. Okay, I can't tell. Did I not? No, maybe. Let me just try running it. So Herbert provided an example of this. It provides a Python programming environment. It looks like it worked. It just worked. And so, yeah, okay, that looks fine. Okay, and okay, I guess we're good. It also contains a pretty amazing integration of one LLM. This is one developed by Google called Gemini. Now, I don't think Gemini is the best LLM for coding. I think there are probably others that are better. I think Herbert in particular, in my experience too, Claude has been really good now. I mean, you wait a month and it changes. So I don't know what'll be better in a month. But I'm not advocating that Gemini is the best one, but this integration of Colab with Gemini is pretty amazing. I'll give you some examples of that. So what we're going to do is I'm going to go through and repeat some of the things that we've done in our system biology class for the sort of the programming sides of things, and show you how you can work with an LLM to solve these problems. And probably the most challenging things we do computationally are the parameter fitting, so generating synthetic data and the parameter fitting. And I think on that one, I'll have one quick take on that. I think Herbert will take you a lot further with that and sort of explore some kinds of things with, LLMs about what you might need to do to get reasonable results, because I think Herbert used the term, it's a partnership. At this stage in the game, it's not the well-trained professional. It's that, graduate student or maybe undergraduate student who comes to you and says, hey, I can help you with your course, and knows some of the stuff, but makes some mistakes. You have to review it. That's sort of where we are today. But, wait a couple of years, who knows? Okay, so I included this because I didn't know how much on Colab we would do. You're familiar with this. You can do, like standard programming stuff. Here's something a little bit more complicated, which, one of the things that we do in our class is, since some programming is required, we do an initial sort of self-check for the students to see, are they really ready for the course? And so the standard problem I give is one with finding prime numbers. It's something everybody's familiar with, the sieve of Aristophanes. And so here's a script that could do it. So you see that we didn't include some of this stuff so much, but there's an if statement. You see a for loop where you can iterate across something. You can stop the flow within the loop, but with a break. And so, it comes up with an answer there. And then the code that we want from the LLMs, so basically the units of interaction that we're going to have with the LLMs, are primarily going to be with functions, not so much with scripts. And so with a function, you've got a name, you've got arguments, and you've got return values. So here's a function that generates primes, or checks to see if something is prime. You give it a number, in this case it's an integer, and it returns a Boolean value, either true or false. And you got a few checks over here. And basically what it does is it took the script and wrapped it with one of these def statements. Instead of printing stuff out, it returns a value. And so, yeah, you can run this in Colab as well. I push this, or it's the command enter. Okay, so that's all the setup. Now let's get on to writing code with Gemini. So you're familiar already with how these notebooks are laid out. It's sort of this notion of what was the term? Writing readable programs. There's a term for this. I've forgotten it already. Literary programming. That's it. Yeah, you're right. You got it. Yeah, literary programming. And the idea was that you could intermix text, create a narrative, as well as computation. And I think that as a way of presenting results, this is great. This really is a very effective thing to do. As a development environment, it's limited. And one of the common problems that you'll run into is that the answers you see that it produces are a result of the sequence in which cells were executed. And if you execute cells out of sequence and then rerun the notebook, it likely will fail, because you have to make sure that everything is in the same sequence as you want it to be executed. One of the most common bugs in code that I would get for courses. So anyway, so with Gemini, the way it works, we have cells that are text cells. This is a text cell. It has a heading. It uses a markdown kind of approach for headings with a pound sign. And then this here is a text cell also, and it just contains text. So we've got, all the basics to work with. So what I've got over here are headings that show you, different tasks that we're going to undertake with Gemini. What Gemini will do is Gemini will generate code at the end of the notebook. So this marker over here, Colab work area, that's or I probably should call it Gemini work area. That would make more sense. So the Gemini work area, that's where Gemini is going to put the answer. And I say this because it's very easy to get a lot of clutter in your notebook and be confused about where you are. Once you see what's in the work area, then you can go back and say, well, I want this function. I'll put it back in my the main area. Okay, so let's write some code with Gemini. So we talked about before about large language models. It's all about the prompt. Okay, I'm sorry, went too far. Here we go. It's all about the prompt. And so we have to figure out a way of asking Gemini to do something. So let's start out with, we're going to do that problem that I said was our self-evaluation problem. So the full problem is a little more than what I described. This was to find, is one number prime? Actually, the full problem is find all the prime numbers less or equal to some fixed number. That's the full problem. So, okay, so here's our prompt. Okay, it is, let's see here, I put it in quotes. Write a Python program that generates the prime numbers up to a specific limit. So, I mean, there's nothing magic about the way I wrote it. I mean, we could write this in different ways. I mean, the fact that it has this language understanding embedded, and I'm going to use the word understanding now, not because I think it really understands it in a true sense, but I think that that's a useful shortcut rather than me putting air quotes around it. I'll just use that freely. So this is what we're going to do. And probably other prompts will work just as well. So the way you invoke Gemini to work with you is, you see this is the, what do they call this? I think they call this the sparkle. So it's at the bottom of your screen there. You touch that and it said, what can I help you build? So that's an invitation to give it a prompt. So I just copied that prompt. Write a Python program that generates the prime numbers up to a specified limit. And then you go. And so this is a common way you'll see it going. So it gives you, it tells you it's gotten started, and it tells you, here's what it's doing. Now, at this point, you can say accept and run. So that means, we'll get to some things that are multiple steps in a minute. So that the accept will make more sense because it's about a step. Or accept means you take all of the steps in place. But let's take a look and see what it wrote before we accept anything. So I think Herbert alluded to this as well. You have to look at the results that it comes up with, because it can skip things. He mentioned the issue he encountered, and it turns out I encountered the same thing, where it didn't do the reset when you're doing parameter fitting. Okay, so a few things which I really like. First of all, it documents. This is something I actually take points off with students, is you have to have, this is called the doc string for the function. What does it do? what is it? What are its inputs? Both the semantics, it's the upper limit, and the data type, the integer. And what does it return? Okay, that's a Python data type, a list. And it doesn't tell me the type, the list of what. That would be good, but it's okay, it's acceptable. All right. So a few things here which are actually sort of interesting. So first of all, it checks to see if what the limit is. So if the limit is less than 2, so 2 is the smallest prime number. Remember, the definition of prime number is a number that's divisible by no number other than 1 and itself. So if it's less than 2, it can't be a prime number by definition. And so that's sort of sophisticated. That's pretty cool. It created that. It's got decent comments in here. And so this is good if you are sort of hesitant about your Python programming. I have found by and large there are good comments in here. Not only is this a way to generate code that you can use, this is also a way of you learning more about Python so that you can be a better critic of what it generates. So create a list of called prime, initializes all entries to true. So these are whether or not they are going to be true. So this is a little sophisticated. This is a Python idiom that allows you to create a list of Boolean values of true that are equal to whatever this number is plus 1. Okay, and it says that 0 and 1 are false because those are not prime numbers. Okay, and then we've got a for loop over here. So this is also sort of interesting. So in class, I know many students will not think that, gee, I don't have to check all the way up to the number, just the square root of the number, because if it's not divisible by the square root, it wouldn't be divisible by anything larger than the square root. So I think that's sort of cute. It was sophisticated enough to realize that in this function range, this has to be an integer. If you do this limit here, you end up with a float. So these are all nitty-gritty problems that, if you're not a Python experience, it'd be easy to find, make some mistakes. And then it's got the various logic in here. The other thing which is very important for doing code with Gemini or any of the LLMs, they generally construct a test. So rather than example usage, I would call this tests. Okay, limit equals 5. So then it says these are the list of prime numbers. Now what it does, it actually is not truly a test because what it's doing is just running it. What you would really like it to do is also check to see if this is correct. So that probably needs a little bit of help there. All right. What happened here? I think somehow we got it generated twice. I'm not sure why. Okay. Any case, so now let's try running it and see what happens. Okay, and so it gives us the prime numbers and we can evaluate this. What I would probably do with this code is I'd probably pick a few of these and, use those as tests just to make sure I got something that works right. So, okay, so fine. Let's say I'm happy with this as is. What would I do now in my workflow? Okay, so that was my question. I think what I would do is I would copy this back to where I was, write code with Gemini. So here's here I would probably just put it in over here and then, have something in here about, author Gemini, something like that. But I think in terms of workflow, you keep in mind, oh, that's interesting. Okay, I don't know why the save failed, but we'll have to make sure we save it for you. So you're going to find that this area over here, this Gemini work area, it's going to have a bunch of other stuff in here. So it's going to give you various tasks. I ran everything. That's the reason why. Okay, let me clean this out because this is ridiculous. Okay. Why didn't that do that? And this. Okay. And this is, that's what's going on here. I did a run all, and as a result, it did some strange things. Okay. And yeah, it did. That's why this is here twice, is I did a run all. Okay, fine. Okay, so this is what I should have ended up with. Now at this point, it's just one cell. one block of code. It's not too bad. But I would suggest just get rid of this. This is your work area. You say what you want from the work area and you go on to your next task. Okay, so let me pause for a second and see if there are, I don't see any questions yet in the chat. There are no questions. I will go on to something a little more sophisticated, something more computational specific. Okay, so let's do some basic modeling with Gemini. Okay, so I'm putting in a couple of models here. I've got this first model here. It's just a simple sequential model. A goes to B goes to C. And what I'm trying to do here, I just want to run the model. So this is pretty basic stuff. Okay, so, okay, fine. So I've got Gemini right down here. Here's my Sparkle, and I type in my prompt. Use Tellurium to run a time course of model 1 until it reaches steady state. All right, well, that seems like, pretty straightforward stuff. Except if you think about it, what's sort of cool about this in terms of the prompt, look how I'm using the name of a Python variable. That Python variable's right there. It's not something that I want it to pick out of its, training data or something like that. I wanted to know about my model 1, not the model 1 that somebody somewhere on GitHub used. And Gemini does that. It has that level of integration. It'll do it. So that is very cool. Let's see what it does. Okay, here we go. Here's the code to simulate Model 1 using Tellurium to steady state. Okay, so I'm just going to close this and take a look at this. Pretty short. Okay, so you've seen this a lot. It did the load A of Model 1 because it's a antimony model. And it does a simulate. Now, this is interesting. I did ask for a time course, so that's fine. It chose to run it until time 1000. Now, how do we know that time 1000 is long enough, or is it too long? It doesn't, really what you want is, something about steady state. So that's sort of interesting. But, I mean, it will produce an answer. So, got that. But that's something where it was a bit less sophisticated. There's a steady state API call in Tellurium. It probably should use that in some meaningful way. Okay, anyway, that's running a model. I'm going to keep that one there, I think, because I need it for the next one. Okay, here we go. All right, so actually, let me go back over here and I will copy this. Let's see here. I think I can just do a right click and copy cell and then go back over here. And then if I say a right click and can I paste? I don't think I can. Okay, that would be a good thing to be able to do. All right, so if I'll just copy the text and then go back here to running the model. And then I want to add code. I will do this. I'll run it again. There's my output. Okay, fine. And of course, we will give appropriate attribution. All right. So, oh, okay. Yes, I know. I'm not doing that. Okay, so let's go on to the next part of this. This is a pretty trivial example, something you could have picked up out of, the read the docs for Tellurium or Stack Overflow. Maybe a little more convenient because we're doing this inside the notebook. We didn't have to go to all those resources, so a bit of convenience, but nothing super sophisticated. All right, but let's do something a little bit more, and this time we're going to do some analysis. So let's take a look at this output. So I see that species 1 starts high and ends up at 0, and species 3 starts low and ends up at the same value that species 1 started with, and species 2 initially is low, peaks, and then goes down. So, this is a simple example. We know what's going on. It has to do with, how mass is being converted along the way. But, this is a great one. You can imagine a more complicated simulation where you're not too sure. Okay, so I'm going to do a prompt, ask some help from Gemini to be able to interpret what this is. Oh, actually, before I do, let me do my thing with clearing out this area over here. Yeah, I need to get rid of this. What did I do? I didn't want to do that. So file, I think it's edit, undo the delete. And then let's see over here, this I want to delete. Okay, so that's good. So now we're back to running a model analysis. Okay, so I'd like to know why it is that explain the time course for species B. Okay, so that's my question. Okay, so again, I go down to my Spark goal. Did I catch it up? Yeah, I did get that. So I don't know. I think I could probably leave that in there. It won't matter. Explain the time course for species B. Now, this is a little more sophisticated. I mean, if you had a complicated model and it was something beyond like, how do I run this model? You know, like, why does it get this answer? You probably have to go to some sort of special forum and show your code, or, you know, find out if somewhere you can find Lucian Smith's phone number, you know, something like that to try and figure it out. So, and here we're going to ask Gemini instead. See what Gemini has to say. Okay, based on the time course, concentration B initially increases, then peaks. Okay, so this is typically these responses. It typically just restates what you asked. Characteristic of intermediate species, and then it talks about how the conversion in from the reaction causes B to rise as there is still A, and then B to fall as it's depleted to create C. So that's pretty reasonable, you know, as an answer here. This is what the answer is that it gave. I think what I would do over here is then I would go back over here and say Gemini answers. I probably would do something like that, you know, and then, okay, fine. So I got an answer to that question. By the way, this is this is the kind of thing I was thinking about in terms of the homework. I see we have one question here.
No, it's a point from me.
Run times. Oh, thank you. Sorry about that. Okay, so it actually only ran it to 100. Yes, you're right.
Yeah.
That's 1,000 points, right? Thank you
That's
for the
right.
correction. Okay. 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 So that was one question that I had, and the kind of question that we would ask in class to make sure people understand reaction networks. Okay. Here's something a little more creative. Okay, this is going to take a little bit more effort on Gemini's part. You see that right now, the way this network is structured, the species B peaks at about time, I don't know, like 5, something like that, I'm guessing. Maybe it's, you know, a little less than that. What would we have to do to change this model, model 1, so that species B peaks at 20? What do we have to do that? That's a little more exploratory, a little more demanding. I mean, actually, that's a credible homework question. Okay, so let's see what happens. What does Gemini have to say for itself? All right, so this is something. Okay. Oh, wow. It gave it to me directly. That's different than what I got before. It's the other thing about these models, they're stochastic. So you ask the same question twice, you may get different answers. Let's see what it does. Accept and run. Okay, and let me get rid of, okay. Pretty close. So the B has shifted. Okay, let me see. Okay, so great. We're okay, so you can see that this is going to be a great opportunity to interact with it a little bit. And Herbert mentioned that the interactions are a critical part of any significant task. So you can see, yeah, it moved it to the right, but it's not at 20. And let's say I really want it to be 20. So yes, it moved to the right, but I want the peak at time 20. Please conduct a search of parameter values to make this happen. Now, I've given it some hints here. I told it what it needed to do. It sort of knew this to some degree. And again, please, you know, air quotes around new or understood or anything like that. But you can see where it's showing me here what it's changed. So the thought is that it actually probably should have included the old value. I think the old values were 1. But so it's making it so that K1 is larger than K2. So let's see what happens now. All right, so finding the exact parameter value to make B occur at time 20 requires a parameter optimization approach. So now we're getting more sophisticated. So they got to define a function to simulate the model. You got to define an objective. How do you know you're at 20? So it's very much like parameter optimization or parameter fitting. Use an optimization algorithm. It's using, I think this is, you used, I forgot, oh, used LMFit. That's right, Herbert.
Yeah,
Okay, but these,
I think LMFit is built on SciPy.
it is. It's built on SciPy. Right. You implement the optimization, verify the result, you present the results. Okay, so that's what it's suggesting that it should do. So I'm going to just say accept and auto run. So what it's going to do at this point, because this will give you an example of something much more sophisticated. All right, so it gets, this is the function to, I guess this is the main function for the K1, K2. And then it's defining an objective. It's giving you that part there. And let's see here. It's giving you basically, here's its workflow. It's giving you each task one at a time. All right. And oh, I've had this problem. Okay. All right. We'll go back to this one in just a second. I think there's a bug there, which is good because we should show where the problems come in. Implement the implementation, verify the result. Let's see what it's doing for verifying the result. Peak time with optimize. Okay, so I'm not even sure it moved it. Okay, so the issue is somewhat like what we had before. We have got to go back a little bit more. Simulated time. I'm looking for, yeah, let's see. Get peak time. Yeah, okay. So I think, no, I want, it's the here's the objective function. So many time you could get peak time. Okay, so the problem is it's doing the simulation over here. It's doing, oh no, it's going to reinitialize. Yeah, it's because it's doing the load of the model each time. But that's that high overhead approach to doing it, but it will work. Okay, and then let's take a look at okay, so the peak time, max peak index, argmax. Okay, so this is finding the peak. That looks like it's doing it right. Okay, and it's got even a little test for that. Okay. All right, it's good. Let's see what it did for. Okay, so let's look at the objective function. The objective function is it gets the peak. The peak is 20. And it's looking for that difference. And what is, okay, so that looks reasonable. Now it's using the absolute difference. Well, that's fine. That really doesn't matter for this. These are scalar values. It's not going to matter. Okay. And then it's using minimize over here. That's fine. This is, we saw Nelder-Mead before. And it's printing the optimization. So what we want to see is, then how close did it get? It's off by a little bit. You know what? The other thing is, let's see how many points it's using. It's using 100 points. So let's see. Let's see what it's doing here in the simulation, because that is another issue with. I want to see where it's doing the simulation. That must be up here. Yeah, it used 100 points. Suppose we did 1,000 points. Could we do better? Okay. So you can tell this requires a little bit of insight in order to figure out what's wrong. Right? I mean, it's, it got us quite a ways, but it doesn't necessarily solve it. And it may not be as simple as using the wrong function. Let's see if we're any better. and this.
Hmm.
Yeah, it's still off. Okay,
worse.
so yeah, it does look worse. I agree with you. So I think I would have to go back and look at this some more. I don't know the answer. I mean, actually, the last time I did this, it gave me something a little bit different and it worked better. So, you know, it goes to the point about it takes a little bit of work to figure it out, but you get a lot of great hints. So. All right, so let me pause on this one because this shows it, you know, a bit more sophistication. See if there's questions on this.
I'm gonna try doing this in Claude, see what it does.
Yeah, exactly. I think that'd be a great idea, and that's the other observation. So, what is our timing? It's 2:30 Pacific. How much? What's our plan in terms of?
How long have you been going for?
I've been going for an hour.
Yeah, you're done. Yeah.
I'm done. Okay.
The model. Could you actually could you paste the model on your prompt? The one for optimizing.
Sure. Okay. Well, I'll give you this. The
No,
one
just
that I've
copy
been.
No, just chat.
Oh, just the model. Oh, the
I don't know
optimized.
I don't know the
Okay,
stuff.
fine. That's fine.
But I need the model though. I need the model.
You need the model. Oh, yes, of course you need the model. All right, so this model right here is what you want.
Yeah, just grab that.
I'll grab that and I'll put it in the prompt. Okay,
I
let you
don't,
take it.
Okay, yeah, all right.
I'll just put it into the chat.
Yeah, and then I need the prompt you use to
Oh, excellent. Yes,
ask
of
it to
course.
optimize
Yes,
it, okay?
right. We want the prompt too. Okay, and let me go back to that. Given that is model analysis. That's this one right here. So there's some things leading up to this. I said you had to. Let me get.
I don't know if it needs that. Do they?
Okay.
No, don't need that.
All right, fine. I'll just
that
give
one.
you this.
Revise the model so that peak is
yeah,
at
that's
20.
it. That's my exact prompt.
Did you ask it to write the optimization stuff or not?
No, I didn't. I
volunteered.
Well, I'm sorry. I did. I gave it a more detailed prompt at one point. Actually, I get those over here. Here's the more. Actually, let me give you the last prompt.
Okay.
So. Okay. I mean, there's a context thing here, Herbert. Let me give you, but I really have to give you both prompts.
Okay, go on then.
Yeah. Let me do that. So I'll give you both prompts. So this is the first prompt I got. Okay, gave it. And then this is the second prompt I gave it. Okay, and there you go.
Okay.
All right, so let me stop sharing and I'll let you take it away.
Yeah, I'll share then. So I'm going to show a couple of things. And just for fun. Let us see if I try that experiment that Joe just did on Claude. So here's the model. Oop, damn. I hit enter by accident. Oh yeah, okay, no, okay. I'll start again. Stop. It really goes on and on sometimes. Okay. Damn. I keep forgetting whether it's a return or shift return on these things.
I know. Yeah.
Okay. Shift return. Here is a chemical reaction model in Antimony format. Oops. Okay. And then can you simulate the model and update the parameter values so that which one? B peaks at time equals 20.
Okay, yeah, let's see what Claude does.
Okay. Oh wow, what a strange. Oh, I should have told it to use Tellurium. Okay, I'm gonna change that. It's quite an elaborate
there's
plot.
a stop up there on your prompt.
Yeah.
Okay. At least there should be. Oh no, maybe there. Yeah, I'm not sure where the stop is. All right, it'll
Okay.
stop eventually. I guess Gemini has a.
Please use the Tellurium simulation to the Python package page to do the simulation.
Tellurium isn't quite spelled right. All
I
right.
know,
It-
I'll get there eventually.
Yeah.
The whole thing's they could probably figure it
my
out. But yeah.
typing these days. It does actually, it's surprising.
Yeah, it does. Yeah.
Okay, here we go.
There we go.
Better. Loading, simulate. So what I'll do is I'll drop this then into
The
let's
spider
see.
or
Yeah, spider and see what it does.
yeah.
Easiest one.
Right. So I mean, this is one of the nice things about the Gemini integration is you get it right there.
Okay, here we go. So this is spider again. So I just cut and paste that entire thing into here.
Right.
And off it goes. Okay, so that's the original, which was peaking
Right.
at about 12-ish. And here
No, that's not bad. Yeah, no, that looks about right.
claims it's peaking at
Yeah, I know. That
oh,
looks
peak time is 19.7.
yeah, okay. I mean, if you gave it more point, you give it
I
a
mean,
you know,
again, it could be a points issue. Let me go to
yeah,
1,000.
right.
Let's go crazy here.
Yeah.
Run 2.02. Yeah, there we go.
Yeah, okay. We can live
was
with
it.
that.
We can
Yeah,
live with
we can
that.
live with that. Yeah.
So I've never done this one before. I don't know if Joe's done this one. He's probably done this one before for practice, but I've never seen this one before, and that did it first time. So
That was impressive.
That was pretty
I
impressive.
agree.
Yeah.
Right. I also like its visualization better. I mean, that's the other
Yeah.
part. So if it's to show you where you are relative to your target.
Yeah.
And that wasn't something we asked for.
No, it goes above and beyond. This does.
Yeah, yeah. The other thing which, we sometimes critique our students is if you're doing a comparison, you have to have plots with the same scales.
Yeah.
And it does
Oh,
that.
yeah.
It
Oh, yeah, it does
uses the
that,
same
yeah.
scales. Right.
Yeah.
And things are labeled. Right. So
So
there's
it's using
a lot.
it's using a
there's
fairly
lot there.
manual method for finding the peak, I think. Yeah, it's doing a manual method. It's like it's almost it's got an objective function here.
Okay. Did it not use minimize?
Oh yeah,
How did it
minimize
do
scalar. It's using something called minimize scalar.
Oh, okay.
And
So now
SciPy
that's another
optimized.
thing I'd sort of point out to others is that
There it is.
if you are a Python programmer and you're using this for Python, a lot of times you learn about capabilities of packages that you didn't know about.
Yeah.
I mean, we've never heard of that one before.
So let me show you something pretty elaborate here. So so this is an initial prompt. There's a typo there. It should be can, but I typed in an. So it says, can you create a Python script that uses the lmfit package to fit a model to data? The model will be a reaction network in the form of an Antimony model. In this case, it's the Michaelis-Menten enzyme model. Use Tellurium to do the simulations and to provide the objective function that you can supply to lmfit. Create a section of code that will generate synthetic data to test the quality of the fitting process. When adding noise to the synthetic data, avoid negative concentrations. For the model using, it says use P, the product. So I gave it the model. It says, I will create a Python script, and off it goes. So what happened initially, so it created it, and I noticed it's creating this thing called a class for the enzyme kinetic model, which I didn't want, and it did that. And I wasn't happy with that because this is for education. It goes through the whole thing, and I said that was very good. I always, keep them happy. I said if I wanted to teach students, it might be better to avoid the creation of an enzyme kinetics model class. Also, I'll avoid the use of if name main. So it's doing this thing here, which makes it hard to run from things like Spider and probably also from notebooks. So I said, since it can't be run easily on a Python IDE, can you recreate the script with these changes as well as typo? It's very immune to typos, I noticed. Okay, so absolutely. Right. Here's a simplified version without that and more suitable for teaching students. Okay, thank you very much. This is all there. Pretty elaborate. There's the synthetic data. I don't see how it clips. It does. Oh, there's clipping the noise there. So it's clipping the noise using a sort of just a brute force way to clip the noise so you don't get negative concentrations. There's the objective function, and then this is the fitting process which you've seen before. Now, this does not work. Actually, I probably didn't try it actually, but I said, oh yeah, then I changed my mind. I said, can you do something similar with the following model with the added feature that a student can pick which combination of species they can use to do the fitting? So the idea was the student could use this code then to explore if they had different combinations of experimental data and how would that affect the fitting process. All right, he said, yes, here's the modified script for the linear pathway with the ability to choose which species to include in the fitting. So it goes through that. Interesting, it has sets the seeds at the beginning, so it's in principle reproducible. That's the simulate model one. That's the generate synthetic data. There's doing the clipping there again. This is the objective function, and now it starts building the fitting code. But here is the bit that lets you did this rather nicely actually. This is called the student configuration section, and it has a list here, species to fit. This is the list of species that will be used to fit the model. It says change this to experiment, and it gives me examples. So for example, maybe you only have S1, maybe you have S1 and S3 and so on. Okay, so that's rather nice. Then it's very, very elaborate, as you'll see when I run this eventually. You'll see how elaborate it is. I said, but then I ran it and I noticed something odd. So one thing it plots is the correlation between the ground truth and the predicted concentrations. And I said one odd behavior. The correlation plots are perfect no matter what the noise level. And it says you're absolutely right. That's a critical observation. The correlation plots are showing perfect correlation. It made the wrong assessment here, though, so it claims to have corrected it. We'll go through that. Claims to have corrected this, but it hasn't, because it hadn't. But then I noticed the residuals were not right either. I also noticed the residuals increase as a function of time. Is this an expected effect, or is it due to the way the noise is incorporated to generate the synthetic data? I sometimes ask it the question rather than giving it the answer. I don't know why. But, it's an excellent observation. This is indeed due to how the noise is incorporated. And what it does then, it modifies the code to allow you to specify the kind of noise you want to be added to your synthetic data, whether it's proportional noise, constant noise, or mixed noise. So it does all that, and it provides a section here and with instructions where you can now specify how you want the noise added. So one of the hallmarks of a suspect model is if the residuals show a pattern, and because they were showing a pattern, and so I asked it to do something about it, which it did. Okay. So I was very suspicious though, and so I said, as a test, I reduced actually the noise, that should be, to 0 so that the synthetic data was perfect. I also supplied all 3 species. The result gave 0 residuals and perfect correlation as expected. What surprised me is that the histogram plot that compares true to fitted parameters showed that the parameter estimates were not very good. So in other words, those plots seemed okay, but the fitted parameters were terrible. Even though I gave it perfect data, that shouldn't be the case. So also LMFIT failed to provide uncertainties with the message warning, blah, blah, blah. This might suggest a problem with the code somewhere. Said excellent debugging approach. This reveals a fundamental issue with the parameter identifiability. So it thought the issue was to do with parameter identifiability. It's not. This system is perfectly identifiable, meaning with enough data you can you can fit all the parameters. But what it then decided to do was give me a whole bunch of code to check for the identifiability. I didn't look through this code. I don't know if it's correct or not. If you run this code, it claims that there's an identifiability issue. I think it's wrong, but I can't tell you why. Anyway, so I gave up at this point because there was so much code that I wasn't going to go through it to look for the problem. So I said, I wrote my own code, which is simpler with the same model and got much better estimates. Actually, what I did, I went to another AI, ChatGPT, which I know gives simpler code, and I asked it to write it, and it got it working correctly. But I claimed I'd written it myself. So I said when I looked at the code it provided, I noticed that the parameter fits it was coming out with, and they were wrong, were suspiciously very exact. So this other code that I got ChatGPT to write was getting it right, but Claude was getting it wrong. And I noticed that the fits were very suspicious because look, they're so precise. The fitted parameters are, within 2 decimal places. That's the fit that doesn't look right. And it says you're absolutely right. Those parameter estimates are suspiciously exact. They're essentially returning the initial guess rather than the final true values. So it tries again, looking at the code. It thinks it's got a problem with the dictionary, so it decides to simplify things. Identifies another problem. In fact, this problem was the one that was the correct one, but I think it somehow didn't do it quite right because it still didn't work. Now I can tell you why it doesn't work. It's because of this line. At this point, I didn't realize that because there was so much code. I didn't want to look over it to check what was wrong. But this was the problem. But anyway, it didn't work. I said, it's actually a bit worse, I said. I also noticed that the fitted parameters don't change with the noise level. Again, are perfect to 2 decimal places. It says, you're absolutely right. This is a major red flag. The fact that the fitted parameters don't change with noise level and are perfect to 2 decimal places strongly suggests the optimization isn't actually running. So it decides to add some debugging to the code. I've noticed this was Claude. It does this, adds debugging code and asks you to rerun the stuff. So there's the code again. I rerun the stuff and I tell it then what I found. So the objective function is being called, but the parameters aren't changing in the call. The synthetic data looks okay. The other red flag is the following message. One was it only did 9 objective function calls, which is highly suspicious. It should do a lot more than that. This actually gave me my own clue as to what was going on. The fact that the parameter changes weren't changing in the call. So now it says, excellent debugging. That error message is the smoking gun. One or more variables do not affect the fit. So I tried again to make a even simpler bit of code. I said, still bad. It thinks now lmfit might be the issue. It's not. I said, I don't think lmfit is the issue. I've used it many times with success. I would continue to use lmfit, but strip or stripe, as I said, strip the code down to the bare minimum. Also, to simplify things, let's not implement the species selection, but fit all 3 species. That will simplify the logic to see where the issue is. You're absolutely right. lmfit is solid and widely used. Let's strip this down to the absolute bare minimum to find the bug. So that's what it did. It's much shorter than it was. And this was short enough now for me to look at myself and actually turned out to be really obvious. It was, where is it?
The reset to origin, wherever that is.
There it is, reset to origin. So this simulate model call, its purpose is to, simulate the model under the current parameter values in order for the optimization to, to work. And if you remember earlier on, we did this as well. And I told you, you must reset the model each time you run the simulation. So you start at the initial conditions again. The word was reset, not reset to origin. Reset to origin resets the entire model back to when you loaded it. Everything gets reset. So the parameter values that were coming in were basically being wiped out by the reset to origin. And it was impossible then for it to do the fit. It was basically stuck at the origin every time. Okay, so I spotted that. So I like to tell it where it's gone wrong for some reason. I treat this thing too much like a human, but I can see now what it is. I should have spotted it earlier. You're using reset to origin when it should be reset. Reset to origin will reset the parameter values back to the initial values. And it says, bingo, you nailed it. That's exactly the bug. Blah, blah, blah. Reset only, and so on. Here's the corrected version. It actually stopped there for some reason. I think I ran out of credits probably. But that was enough. I got enough information. I went back to the original model it built, checked that. That's where it had the same bug. And then I pulled it into Spider, and this is the Spider model. I've got it now. So if I scroll down, this now has the proper reset in it. Okay. And let me go down to the configuration. The configuration stuff is here. So I can configure the species, and I can also configure the noise. Everything's there. So let's run this, and I'll show you what it gives. I'll clear all the plots, run this. Okay, so it does two things. First of all, it shows me the 3 species fitted, and it shows me the true model, the fitted model, and the synthetic data. I never asked for that. But it gave it to me anyway, which is nice, of course. So the dots are the synthetic data. The red is the fitted model, and the blue then is the actual ground truth. Okay, so the fit is pretty good. But more remarkably, it did this. So what it's doing here is plotting a whole bunch of stuff. Most important is the residual plot here. Plots the residuals, so you can look for any patterns. It plots the correlations of the observed data, the experimental data with the fitted data, which is a nice diagnostic, I guess. And it fits the final fitted plots here. And then this is rather nice. It plots the ground truth parameters versus the fitted parameters. So you can see it's, pretty close, right? They're pretty close. And so this works. So now once you have this, you can start playing around with it. So for example, let's say we only have species S1, right? So we're a poor lab, we can't measure S2 or S3. We just measured that one. And now, of course, it's only showing me 1 because that's the only the data it's got. And now you can see we only have 1 correlation, of course, but you can see now the parameters are quite off. In fact, these ones are really bad. The fitted ones are almost close to 0 when they shouldn't be 0. This one's pretty far off.
Those are later in the chain, I think, right? If you only have S1, doesn't know anything about S2 and S3.
Exactly. It's
Yeah.
about information transfer. Yes, about the amount of information that's present in each of these different species. Yes, exactly. And the middle ones tend to be better, I think, because they tend to experience both ends. Although it's actually not that better, though. Yeah, that's not great either. So
How do we do with 3?
let's do 3. Yes, that's a good idea. Let's try that. We do 3.
Interesting. Very interesting.
If I do 2, things get better, of course.
2 and 3?
Yeah, that's 1 and 3.
Oh,
So
1 and 3.
So that's pretty good, yeah.
Yeah,
So
that's
you
not bad.
don't need the middle one, basically. So this is what I was talking about before, that you could run in silico experiments to see, you're working with an experimentalist to see really what data is the most important to collect, because they may be tempted to collect data that's actually not relevant, not important to the fitting process, and it's better if they focused on other things, which are. So I just show you here, if I switch this to the noise to proportional, which is what we normally use, you see the residuals, they sort of expanding. They start low and then they get bigger. That's not, you want to avoid that if possible, but it still does the fit okay. And the other thing it does, it prints out a nice report, text report here, with everything. Let's see, so it starts here. So these are the initial parameter estimates. This is the results we've seen before from LMFit. It gives all that information. Gives some extra information here, which it pulls out itself. It has a nice little table doing a parameter comparison. And then it runs this identifiability diagnostics. I haven't looked at that. I don't know if that's right or not. But anyway, pretty amazing what it can do. Now, ChatGPT, you can do this with ChatGPT. It tends to produce simpler code in the sense that it does what you ask it to do and doesn't do more than that. But the code tends to be simpler, and so that's why I switched to ChatGPT to produce a simpler code that I could test, and that did work fine. ChatGPT got it right first time. I used it as a means of getting simpler code, and then I used it to fix the Claude code. The Claude code was doing lots of stuff. But there's a danger here, of course. There's so much code here. It's really hard to know whether it's getting it all right or not. Now, I suppose you could ask it to write, test code, unit tests, and so on to verify that it works. The one thing I have noticed, if you ask these things for a lot of code, you then feel obliged to figure out if it's correct or not, because there's so much of it, and it's hard to do that. And then errors creep in, and they compound as you generate more and more code, and so I'm not sure what the right level is, but I mean, amazing what it can do, right? So, I mean, it would have taken me quite a while to write this myself. I spent 10 minutes, I guess, going round and round with it, trying to fix the error. I fixed it in the end. That was still a time saver because it would have taken me, a couple of hours to write this. Instead, it took me 10 minutes. Okay, so, and it appeared to work. Okay, so, that's the demonstration of that. So.
Just a couple of thoughts. So tacking onto the thing about tests, I think with any code, you'd want to sort of explore it a little bit, whether you wrote it or, a student wrote it or whatever. So I think that would probably be additional piece of work, whether, the AI does that or that's another question. Then the other thought is that one of the things I found rather surprising was with the Gemini integration into the Colab environment, it would actually find and fix bugs. Now, these bugs were typically not incorrect answers, like you were getting incorrect answers. But if, for example, in some of the work you showed earlier with parameter fitting, there were exceptions generated from arrays of the wrong shape. And it would find these issues. It would recognize the exception and fix them.
Right,
so those kinds of things it was good at. Yeah.
I mean, ultimately, it seems you need to use a combination of tools. So it's like streaming on TV. You have to get multiple subscriptions to get a decent set of stuff to watch on TV.
Yeah, that's very true.
By the way, I haven't subscribed to any of these. These are all free tier level AIs. So I ran out of time on that. You noticed on the Claude one. I noticed that the free tier has a fairly limited memory as well. Eventually, it'll just say, this is too big. You'll have to start a new chat, and then you start a new chat and just forgotten everything. Maybe the subscription will give you a longer memory for it. So, but anyway, that's it. So I don't know if anybody in the audience has any experiences with using AI. I think there's a lot of potential here. You just have, like most new things, you have to be careful. I mean, we have an active research project to automate annotation of models using AI, and that seems to be quite promising. So the other thing we really love is for it to generate models for you. We have some ideas on that, but we haven't got anything yet to show. So one thing I remember trying, was it over a year ago, design a model that will show oscillations, and this was a chat GDP. It was terrible. It was absolutely hopeless. So it varies a lot from what it's good at. I guess it depends on what it's seen. I've had some amazing experiences with algebra, math. Like for a class I do, I needed to solve some second order differential equations as examples, and I didn't want to do it myself. So I asked, it was ChatGPT to do it, and it did an amazing job. It made one mistake. Again, it was a partnership. I couldn't rely on it 100%. I had to check everything, and it made one mistake, which was factoring a quadratic, the simplest thing for some reason. But the rest of it was perfect, and it got the right solutions. The nice thing is, unlike Mathematica, for example, although maybe Wolfram will do it, it gives you all the steps in its derivation. So you can trace how it did the derivation, and if there is a mistake, you can pick it up. But that
And you can also ask questions about the derivation.
I was absolutely amazing that it could do such sophisticated algebra, given it's just a token ahead text processor.
Right.
So
yeah, I had a similar experience with something I was looking. I wanted to understand the derivation of something called differential entropy. I wanted to know if a particular property held what's called the asymptotic equipartition theorem. And I wanted to know, does this apply to differential entropy, which is about continuous distributions? And it gave me a nice little proof of it, which was very understandable.
Yeah, it's amazing. So if anybody's got any other examples, great tool, just use with care.
We've got something here for Edgar.
Oh, really? If you use ChatGPT and want to ask something specific about a code or software, and you give documentation of Tellurium, i.e. results improve a lot.
Okay, so this is like sort of a RAG approach. What documentation do you give it? Because there's a lot of different sources.
You just point
manuals. So you just point it to like read the docs?
Yeah, just give it to the URL or what?
ChatGPT is one of the tools that it implements MCP, the protocol to use other tools. And one of the first tools was URL traversal, URL browsing.
Yeah, they say they just give it the URL.
Okay, that's great.
That's surprising because I would have thought it would have read the manual already, but I guess this.
Well, they will have it in memory and just look like that primes it to look at that section. It's like, this is important.
Okay. Yeah, right. Okay, that's good to know.
One of the things I'm sort of curious about. So in that case, and so I guess this is back to Edgar, who offered us this information. In that case, do you know how it accounts for tokens? Because obviously the tokens I give it with the URL, that's really short, but it's got this huge document which is the target of the URL, and I don't know how they account for tokens or usage. I don't know if you know anything about that.
Even PDF that's available.
Okay, wow, that's interesting. I wonder how it does the accounting for that. Okay, interesting.
Yeah, that's good to know.
Okay,
great, thanks. Yeah. Okay, any other comments?
Any comments or thoughts? We're definitely down to the final diehards here. Yeah, hardcore.
Yeah. Okay. Well, if there's no comments, we can close the session if you like.
Oh, here we got something else from Michael.
I need to download Earth paper on the models.
Oh, on the models, do you mean the LLMs? Is that what you mean, or do you mean the?
I try to feed GitHub also. It does work too.
Oh, wow, the interesting.
Yeah, what's the download Earth model? Down to Earth.
Just-
Oh, I see. A down to Earth paper on models.
Paper on,
Yeah,
like,
right,
on
so-
these
you're-
LLMs.
Well,
yeah.
unfortunately, we're not LLMs, and so our parsing is imperfect.
I tried to write a little short book, Introduction to Modeling, Modeling Systems. So it's supposed to be an intro book. It's only 100 pages. Let's see if I can finish it off. But yeah, there does need to be something simple that explains modeling a bit. So maybe you've encouraged me to continue with that. Actually, if you send me your email, maybe I can send you a copy to see what you think.
Yeah, if you use the website, right, that's not pricing, but it will limit the number of tokens you use. Yeah, I mean, you're not paying for it because it's free tier, but like Herbert ran out of usage because he typed in too much.
Yeah. Yeah, Claude seems to have a limited memory span. It's about on per chat.
Right.
Seems
Okay.
unfair
Oh,
when
great, thanks.
you're using all your tokens just to debug the mistakes that it's made, right? But
Yeah. Okay.
Okay, got your email, thanks. I'll send it in a couple of days, okay? All right.
Yep, we're done with
Yeah.
this, I guess.
Yeah.
Oh, here, one. Okay, yeah. Okay.
Yeah, we got yeah. One thing we keep threatening every year is to do short, focused sessions, as in other times of the year, like 3 hours on some topic. Keep threatening to do that. We don't do it. We'll do it one day, I guess.
that's right.
Yeah.
Good.
One thing we would like, I think there will be a post class survey that we're going to send out, a relatively simple thing. If you have a few minutes to answer that, when you have a chance to digest what you've heard and what you found most valuable, that will help us in the future.
Yeah, and it's completely anonymous.
It's completely anonymous.
So we can use this information to support the center, because the money comes from the NIH. So. Yeah.
All right.
I'm sending you something, okay?
Okay.
By email?
I feel like I'm on the last day of a cruise and everybody's hugging and kissing goodbye.
So, Hunter, did you get my message?
Yes.
Good.
I did.
Yeah, right.
All right.
All right.
Okay.
Great.
We talked about a wrap up at the end or beyond the AI? This was discussion. I don't
No.
know if there's anything else. Okay.
No,
I
I think
guess
we're done. Yeah, I think
okay. We're done. All right.
Good, yeah. That's great. Good.
And
It's
then
Friday.
Yeah, and it's Friday, right? And some people are in time zones where it's already Saturday. So
Yeah, right.
And one last comment here is if you missed any part of today's session or yesterday's content is already posted on our YouTube channel. And we'll send out an announcement to everybody with links to the YouTube channel on Monday.
Okay, good.
great, thank you,
Yeah.
Hunter.
Yeah, okay.
Oh, and you're gonna save those, I guess the chat stream from
Yes.
today.
We'll save
Excellent.
We've got the recordings.
Okay, then that's good. That's a lot of great material for them. Okay, we're down to 10, which I think half of them is us.
Okay.
So,
All
Probably,
right.
all right.
I can go ahead. I will stop the recording.
Yeah, stop the recording.